Good morning. Here you are. Okay. Well, welcome to the second day. My name is Francesca Dominici, and it's really my pleasure. I'm going to introduce our speaker for this morning. I know Liz Stewart for a very long time, maybe around 20 years, from Hopkins. So actually, I was looking at Liz graduated with a PhD in statistics from Harvard in 2004, and then moved to Hopkins. Had a brilliant career at Hopkins, and now she's the Frank Hurley and Catherine Dorier Professor of Biostatistics. So she's the chair of the Department of Biostatistics. She's also a Bloomberg Professor of American Health, a faculty member of the Johns Hopkins University Data Science and AI Institute, and before being appointed as chair of the Department of Biostatistics, she was also vice dean for education at the school. She has a very extensive CV and a tremendous amount of publication, high impact publication. Among her area of research is mental health, policy evaluation, causal inference, external validity, and many more that you will learn today. And also, just a personal note, I'm going to embarrass her a little bit, but in, 2009, I remember hiring Corey Ziegler, that I know is here. Corey, yes. So Corey introduced me to causal inference and started to tell me about all of the stuff about propensity score. And I said, oh gosh, now I hired this postdoctoral fellow that, he's telling me I have to do all of this causal inference. And so I needed to learn. And one of the best paper was one of the introductory paper that Liz Stewart wrote on propensity score. And it really set the path for me from 2009 where I am now. So thank you for doing such excellent work, Liz. And now the floor is yours.
Thank you so much. It's really, really great to be here, and thank you for the lovely introduction. Francesca was like a couple years ahead of me when I was like a new assistant professor, and it was wonderful to have her setting the path. And I am, this is a little secret, I was one of the TAs that Fabrizia worked for with Fabrizia back in the day. So it's really nice to be here. I apologize that some of you have actually heard pieces of this talk before, and so maybe you'll get something new. But I'm also going to try to take a bit of a step back. It's a bit awkward giving this talk because many of you in the room actually know more about some of the technical details of some of the methods I'm going to talk about. My goal is to kind of convey some of the challenges that come up in practice and sort of how do we think about this work really is motivated in sort of medicine, public health, and some of the areas I work in. So hopefully it will give some food for thought, I think, especially as we think about how to help have our methods be used in practice and sort of, we might come up with all these great new methods, but then how do we kind of adapt them, use them in sort of real world settings for good use. Okay. So the title, again, is sort of Integrating Data for Causal Inference, and I'm going to talk through a sort of specific case study. But before I do that, I wanted to give a little bit of context for some of my interest in this area. And this comes about from a variety of things, both my kind of research world, day-to-day, and then also in the United States, we have the National Academies of Sciences, Engineering, and Medicine. And I serve on two kind of standing committees for them, including the Committee on Applied and Theoretical Statistics, and then also the Committee on National Statistics, which is sort of more about federal. And in all of these worlds, I just keep hearing interest in data fusion, data integration, multimodal data, sort of all of these buzzwords. You can see here just like some PubMed trends. PubMed is like medical papers, but a lot of methods things too. Interest in sort of data fusion, data integration, On the bottom are 3 examples of National Academies reports. You can't see the details, but one is on data integration for traumatic brain injury, integrated system of US household income, wealth, and consumption data to inform policy and research. And then when I worked on the right, toward a 21st century national data infrastructure, enhancing survey programs by using multiple data sources. So kind of this idea of like, how can we supplement large-scale federal surveys with administrative data and other sources. So there's just, I think, a growing awareness that there's lots of data sets out there in the world, and we want to try to combine them somehow for sometimes causal purposes, sometimes other purposes. There's also kind of at the same time some large-scale efforts that I'm going to sort of put in this bucket of combining or integrating data. These are just 2 examples in the US. One is the All of Us study. How many of you have heard of All of Us? Okay, not many. It's sort of like the UK Biobank, and the idea of it is to try to be nationally representative in the US, but it is not formally representative. And they're kind of getting all sorts of information on millions of people. So, surveys, they're also merging in with electronic health records. It's sort of a whole mishmash of stuff. On the right is a project that I'm involved in at Hopkins called ECHO, which is, again, a huge NIH-funded project called Environmental Influences on Child Health Outcomes, where this one, just as a little backstory and just sort of historical context, years ago, the US tried to set up what was called the National Children's Survey. So it was going to be a nationally representative sample of children in the US, followed for a long period of time. That fell apart for various reasons. So now there's this idea of, oh, there are existing cohorts, bless you, that already exist in the country. And so the idea of ECHO is to combine all of these cohorts. It's sometimes called a cohort consortia, bless you, or I learned another term recently. But the idea is like, okay, we've got a cohort of kids in Nebraska and a cohort of kids with autism in San Diego and a cohort of kids in New Hampshire. And we're just going to combine all these, harmonize all these data sets, and that will help us learn more than we would have learned otherwise. Not formally representative, really used for like a whole variety of research questions, but sort of just this idea of like, if we create this data set, this combined data set, good things will come. And partly I'm kind of talking about these because these are both huge, like, dollar investments. I mean, I don't know, I didn't look up the actual prices, but millions and millions of dollars. But again, there's sort of these, and I'm not using either of these as examples, but really just wanted to sort of introduce them as this sort of, this is a huge growing area. And I think a lot of people, and I'll focus on causal stuff, but also for non-causal purposes, haven't sort of thought through, well, how do we actually use this data? And what do we do with it once we kind of put it together? So part of that, and again, the topic of the talk, data integration for causal inference, is huge. I'm going to be talking about sort of a specific piece of it, but again, just wanted to set the stage a little bit with sort of this whole spectrum that I see in terms of what is meant by integration. So one level, and I've been in meetings where, again, sort of this whole spectrum is covered. So one level might be literally just, we have a cohort of people and we merge in geographic identifiers, and we sort of merge in information about other contexts of where they live or what they do. So sometimes it's really just a matter of like the same people, but merging in different variables. There's also, of course, a huge tradition in meta-analysis where maybe we have studies and we combine results from studies. And again, people in this room are much more experts in meta-analysis than I am. What I'm going to be focusing on for this talk is sort of that third bucket, which are ones where we're really trying to combine data on individuals. And so we might be combining these cohorts like ECHO and All of Us I talked about. It might be individual patient data meta-analysis where we are actually using individual patient data from the studies. Federated learning is a big thing right now. I can come back to that. And then in the sort of pharmaceutical world, there's this push around real-world data and external controls, and even sort of like using data data on people receiving a new treatment and sort of merging in data from a registry or some other administrative data source as a control group. And then finally, and actually this bottom bucket is something I'm quite interested in, but nicely is going to get covered more by the next session. So I'm not going to talk about it in this talk, but I'll come back to it in the next session, is sort of weight of evidence, sort of synthesizing evidence where we might be sort of, it's actually, maybe I should have put these in a different order, more like meta-analysis where we're sort of combining different sources of evidence, but kind of on the back end. So again, today I'm mostly going to, or this morning, first talk, mostly focus on sort of that third category of combining individual data in different ways. Okay, so that's kind of the lay of the land for, in some sense, for kind of this broad data integration world. I then wanted to turn to, this is a symposium on causality, so I wanted to turn to some of the specific use cases for causal questions. And again, you've heard some of this yesterday. Julie, who spoke yesterday, has a really nice paper on this. So again, I'm not the only one working in this area by far. But it was occurring to me that often, again, there's sort of these buzzwords around data integration, data fusion, et cetera, and there isn't always a clear articulation of what is the goal of any particular case. So here are some of the kind of cases that I've come across where we might be integrating data for causal purposes. One is this area of sort of assessing randomized trial generalizability. So Julie, myself, others in this room have worked quite a bit on this, where the idea is we combine data from a randomized trial and information on a target population of interest in order to assess how well the results from the trial might sort of generalize to that population. But where we don't have like treatment effect estimates in the population, like we don't have treatments yet in that group, so it's really just sort of equating the covariance. And I'll come back to that a little bit. But so that's one possible use case. Another is, bless you, use case like I briefly mentioned earlier on this idea of external controls, where there's a long history going back to Lalonde that we talked about yesterday of taking a treatment group and finding another source of data that has a comparison group in it and sort of using it that way. This, by the way, if some of you are not in sort of pharma, FDA kind of world, this is becoming more and more common. And just as an aside, one of the things that is annoying about it, they don't seem to recognize like, oh, this is really just a non-experimental study, and there's decades of research on how to do non-experimental studies. It's sort of, they're kind of rediscovering some of that. But that's another use for sort of this integrating data. There's also a history in causal inference of sort of bringing in an external data set, or, well, information on the same people, but where you have additional information on a subset. And so that's a way to basically adjust for more confounders. And there's technical approaches like propensity score calibration, where again, the idea might be for a subset of our group, we integrate some additional data on maybe more intensive measurements of their environmental context, or we link them to some external database, things like that. So we can basically measure additional confounders on some of our people by bringing in this additional data. There's also, of course, a long history, and Jose is here, Paul Rosenbaum is really, I think, very thoughtful about this, about using multiple control groups and integrating data to sort of probe the consistency of effect estimates. And sometimes that's done informally, where we might kind of have multiple control groups and run an analysis multiple ways. Other times there's more formal approaches for that. What I'm going to be focused on today is sort of the bottom two bullets. So again, kind of giving you big landscape right now and then turning to this case study, is interest in increasing statistical power. And so I'll be talking today about, small randomized trials, but then how do we integrate large-scale, non-experimental data to kind of balance that. And the broad term for this, I think, is sort of this idea of what is sometimes called cross-design synthesis, which honestly sometimes kind of overlaps with the first bullet. Like sometimes the goals are not super clear, but I think about cross-design synthesis as cases where we actually have, say, experimental effect estimates and non-experimental effect estimates, and we are combining those together and sort of integrating across. So hopefully that kind of makes sense. Again, broad landscape, and I'm going to mostly today be focused on the bottom two bullets. So this is all great, but one of my themes is going to be what are some of the catches? And again, I'm going to talk through some of this within a particular case example. But my hope here is to sort of help motivate interest in sort of thinking through some of these challenges by this sort of crowd. So huge issues of measurement differences. And I am not the first to discover this. There are huge fields of data harmonization and approaches that are designed to try to deal with that. But when you get into individual studies, you just realize like how hard it really is. I will just talk through a couple examples briefly now, and we'll see more of an example as we go along. This Stewart and Rhodes paper, we were doing a study of generalizing a randomized trial to a target population. And it was in the field of early childhood education. So the trial was a study of Head Start, which is a program for like 3- and 4-year-olds. Huge data set, like 500 variables, and like so much detail on these kids. Our target population was actually Head Start participants, a sort of a national survey of Head Start participants. Also, like 500-600 variables, sort of baseline variables on these kids. There were literally 6 variables that were consistently measured between these two data sources. And even like the race variables, of course, were different. The most frustrating was like they each had like classroom observation measures where they would sort of have measures of what was happening in classrooms. Really important for studying early childhood education, but they had different classroom observation scales. No validation to go across, or perhaps even more painful, they might have had the same scale for a couple, but like they standardized it differently, or sort of they were on different scales. So in the end, we could use 6 variables to, and maybe, we could have like gone in and really tried to like figure out were there more, but the amount of work required to understand that was intense. So again, one case example, and I'll talk it through a little bit more later. And what part of the point here, and we'll see this in the example I talk through, usually these studies are designed for different purposes. So a randomized trial, for example, often is interested in like short-term, sort of more proximal outcomes. In administrative or sort of large-scale data, we often have more long-term outcomes. So it's not that either study did something wrong. They just had different purposes that are not aligned necessarily with combining. Okay, so that's one issue. Another are sort of just underlying population differences. And as causal folks, I'm sure many of you in the room are like, oh yeah, combining like a treatment group with an external control, that can be very challenging. They might come from different geographic areas. They might be different underlying sort of health populations. So like ECHO is this example where we're kind of like, it's this whole hodgepodge of like cohorts. And many of the research questions sort of want, like there was one paper on the effects of prenatal tobacco exposure, like secondhand smoke exposure on kids' birth weight. Okay, general question, there's different cohorts we could use to look at that because they have that sort of data. But again, one is like kids with autism in whatever city, another is other kids, and it's sort of like how do we really make sure we can adjust for these population differences? And then third column is data access, that even with all of these efforts towards data integration, it is still difficult to access data sets. People who run trials, like yes, theoretically they need to make it available. It's often very hard to get access. The documentation is not always great. These federated learning approaches are ones that, I don't know how familiar all of you are with federated learning. The idea of federated learning is that instead of sharing individual level data, analyses are run sort of in each place, and then sort of some sort of summary is combined. And it can work quite well when sort of the math works to do that combining, but there's a lot of analyses that you can't do in a federated context. And then just, again, the huge time and effort required to create harmonized data sets. So even if we can get this data access, the amount of substantive knowledge and expertise and time required to integrate them well is daunting. So again, I'm not really up here just to be depressing, partly trying to be motivating of like, we need some methods advances. And oops, there we go. And I'm now gonna sort of turn to this case study to talk through sort of what this can look like in reality, or sort of in one case. But again, I wanted to sort of lay out some of this landscape to think about more broadly for this group. Okay. And again, apologies, because some of you have seen some of this before. So this case study is about essentially, it's sort of one of these projects that I sort of in graduate school had worked mostly on non-experimental studies. And then after graduate school, I worked at a public policy research firm where we were doing large-scale randomized trials. And I sort of understood then very well like the strengths and limitations of both. So this is one of these nice projects that it takes you 20 years to actually come to fruition, is really kind of how can we combine these to like get the best of both worlds. Okay, so I don't think I need to introduce the idea of causal inference to this group. It's covered very well. The context here is sort of similar to Michele's talk yesterday, where there is also sort of in many areas of science this growing interest in personalized medicine, personalized public health. I do work also that sort of straddles education research. There they use this term, what works for whom. Actually, they've changed it to what works for whom and where. Underlying this is an interest in treatment effect heterogeneity, also known as effect modification or moderation. Essentially, do treatment effects vary across individuals? And again, kind of the holy grail is to use that to inform treatment decisions for individuals. So the estimand that I'm going to focus on, or estimand I'm really going to focus on today, is the conditional average treatment effect. This came up a little bit yesterday. So here, we're going to be interested in basically a model of treatment effects as a function of covariance X. I'll get to this towards the end. Yeah, this is like sort of one of the tensions here, is that the goal is really sort of individual predictions for future patients. Let's say this is what we can actually estimate. So we'll see. Okay. So again, the kind of context, which I'm sure this room knows well and is already thinking about, is that one of the challenges is that randomized trials are wonderful. They are unbiased for causal effect estimates. I'm setting aside noncompliance, missing data, et cetera. The challenge I'm focused on here is that they are also basically 100%, 90% of the time, 99, powered to detect overall main effects. And in fact, they are just barely powered to detect overall main effects. So you have clinical trials in medicine, studies like in education. They have just enough patients enrolled to have sort of sufficient power for kind of an overall main effect. It is much harder, much more data is required to estimate conditional average effects. Rule of thumb, again, total rule of thumb, which statisticians don't often like giving, but that if you even just have two subgroups, like old and young, you need a sample size 4 times as large to detect difference in those effects than for the overall main effect. Okay, so trials are unbiased but small. Observational data then, the question is, can we better sort of bring in like large-scale electronic health records, like once a treatment is out sort of being used, are there ways that we can bring in that data to provide additional information on these conditional average effects? So the challenge there, of course, is there's confounding. The people who are choosing or getting the treatment are different from those who don't. but it is larger and often more representative of target populations and sort of real-world use. So what I'm going to be sort of getting into is, this sounds good, but what does this mean in practice? How much benefit do we really get by trying to combine these data sources? And I will give you, I have to apologize, in reality, I'm mostly going to focus on combining randomized trials, partly because of some of these challenges in bringing in the EHR. So I'll come back to that. Okay, so I'm going to really quickly review this. My goal here is not to read this, actually, because as you can see, so my former student, Carly Lupton-Brantner, who's now at Duke, did this nice review, because this was one of these times where we wrote a grant to do this work, and in the time between submitting the grant and getting the grant funded, the field just blew up in terms of papers. So I don't mean for you to be able to read this. This is just an example. She ended up writing a review paper on different methods to estimating the CATE using multiple studies. And here's just like one part of that paper where you can see like a ton of papers published between 2018 and 2022. And so suddenly it was a very full space. So what I do a lot of is sort of that combining, or sort of synthesizing the literature and trying to sort of think through, okay, what are these different papers doing? And if you dig into them, there are subtle differences between them. Some assume individual patient data, some use aggregate, some use randomized trials and observational data, et cetera. So we were trying in this paper to just sort of give a landscape for these methods. And again, so this is sort of summarizes some of that. Sorry, it is getting warm in here, so I'm going to take my place. You can see sort of some of them use aggregate level data. I've talked some about some of those challenges. Again, federated learning, I mentioned briefly, and then some use individual patient data. There's also sort of a distinction between parametric models and non-parametric models, as you might expect. Some of them are sort of like, you can imagine a typical meta-analysis or individual patient data meta-analysis, like a linear model with random effects or fixed effects. Sorry, actually, let me take a step back. This is one big distinction, and I'll come back to this, because essentially the typical previous approach was sort of parametric models. Like, okay, we think age is a moderator, so we're going to put an interaction between treatment and age into our model and see what happens there. The newer non-parametric approaches, like causal forests, developed by folks in this room, and sort of other machine learning approaches, don't require that sort of pre-specification of like age. So they have this nice benefit of being able to sort of identify the interactions that exist without sort of having to pre-specify. They can be more challenging to interpret, and I'll come back to that. But again, they are sort of more flexible. So I'll come back to some of these in our case study. Okay. So again, what I'm going to focus on here is combining individual patient data from multiple randomized trials and asterisk observational studies to estimate the conditional average treatment effect. And again, partly trying to just sort of get a sense of how all of those 20 new methods that have been developed, how do they work, and kind of how do we think about using them in practice. I want to give a big caveat, and yesterday we had a discussion about Bayesian and such. I was trained very Bayesian, which is the irony. And so we, as a research group, are also exploring various Bayesian methods for this. That is not what I'm talking about today, and my former postdoc, Kwan Yi Hong, is really leading that stuff. But I want to acknowledge that there's actually some really nice opportunities there. They're just not my focus today. Okay. To get to the motivating example, so I do, most of my work is in mental health, well, not most, a lot of my work is in mental health and substance use. So this is motivated by an application around treatments for major depressive disorder. And in particular, a few years ago, a new medication called vortioxetine came on the market, and we were interested in examining whether sort of one of the more standard second-line therapies, duloxetine, how vortioxetine and duloxetine compare. One interesting just side note is that what happens a lot of the time, at least in the US with the FDA, the pharmaceutical companies had to do trials of vortioxetine when it was going to come on the market. They did 3-arm trials of placebo, duloxetine, and vortioxetine, but all the publications only compare each medication to placebo. They don't actually compare the two medications directly, because the goal for the regulatory decision is just should vortioxetine be approved. They didn't have to prove that it was better than the existing duloxetine. So we are interested, so basically both of these are shown to be better than placebo, but there's less known about how they compare with each other or whether there is differential effects for different patients. Okay, so the trial data we have is from, this is, at the end of the slides I have a little disclaimer. There's a website, yeah, it is a website, a group called Vivli, which does provide access to randomized trials. Pharmaceutical companies sort of put their data up on Vivli, and then researchers can apply for access. So that's how we got these trials. So there were 4 trials, each about 400 to 600 people, with, again, this sort of 3-arm. I'm setting aside placebo today. And in general, these trials enrolled fairly similar populations in terms of their major depressive disorder. This MADRS score is sort of a measure of depression severity. And so there is some threshold for that. I didn't say this on the previous slide. These medications tend to be sort of a second-line therapy, so they often are given to people who haven't responded well to sort of their initial depression treatment. And again, as I alluded to earlier, the trials, their primary outcome is the change in this MADRS score from baseline to the last observed follow-up. And again, I'll come back to that when we come to the EHR. Okay. So again, my goal here is not to get into the details of the statistical methods, because other people in the room are better at that, but I'm just going to give you a flavor for kind of how they work and how we sort of extended them. Some of them were already extended, but how we sort of extended them to deal with multiple studies. So actually, let me just go straight to this slide. Essentially, for Kate estimation, there's a few primary approaches. I will very high level summarize them here. And there's this nice Kunzel paper that really goes through it more. Basically, the idea is, okay, 2 ideas. One is we can fit models of potential outcomes as a function of covariates. The S-learner fits like one big model that has treatment indicator and covariates and sort of comes up with, sort of fits that, usually actually more of a parametric approach, but where there's like interactions between treatment and covariates. The X-learner fits fully separate models in the treatment and control groups, gets predictions there, and then combines. So in some sense, the S-learner with all interactions is pretty much equivalent to the X-learner, but that's one difference. And then there's sort of more machine learning-based algorithms that essentially target the effect heterogeneity directly. So the S-learner and X-learner kind of identify effect heterogeneity sort of as like a after effect in a sense of sort of they model the outcomes well, and then there may or may not be effect heterogeneity identified. These, like causal forest, is splitting trees with an optimization criteria that is sort of targeting effect heterogeneity. So it's a little bit more fit for purpose in a sense, where it's sort of designed for this purpose of effect heterogeneity. And again, one of the things we were doing was combining across studies and thinking through how do we use this with multiple studies. So I'm going to just quickly summarize those aggregation methods. This first one, surprise, surprise, doesn't work very well, but people do it sometimes, which is basically just we have 4 trials, let's just put the data all together and then run our models, etc. Okay, so just naive pooling. Next approach, okay, we can probably improve on that by at least like adjusting for study and saying like, well, I'm just going to treat study basically as a covariate. So it's just an additional covariate is sort of what study are you from. Then there's sort of more complicated aggregation methods, in particular augmented ensemble forest where you sort of, it's a little hard to explain, but you basically, you fit a model in each trial. You get, say, 4 conditional average treatment effect models. For each person in every study, you use that model to get predicted effects for each person, and then you sort of summarize across those. So it's kind of an interesting, that's sort of related to federated learning approaches. So in our case, we have 1,600 people. We get 1,600 times 4 conditional average treatment effect estimates, and then we fit some model on those to sort of get common patterns. So if the models in each study are very similar, then at the end, you're going to get sort of something similar. Whereas if the models are very different, like if my effect estimate is very different across the 4, then the sort of aggregate model is going to show that there's not much signal there. We also are going to compare with just a parametric individual patient data meta-analysis where we pool the data and fit a parametric model with interactions between treatment and covariate and and random effects for study, basically. I am not going to talk about the details of this simulation study because simulations are not the most exciting or interesting, but I want to highlight a few pieces of sort of conclusions. A couple notes just quickly. We sort of, not surprisingly, varied the amount of heterogeneity of the treatment effects across studies. We also varied whether the actual true model was linear or nonlinear. We kept our trial sizes about the same as our data, and then we explored also the number of trials. Okay, let me actually just go here. Okay, not surprising. The first approach of just pooling all the data and forgetting that they came from different studies doesn't work very well. But that's going to be a problem as I move forward, so hold on to that thought. What I find gratifying, actually, is that the trial indicator approach actually is pretty good. Sometimes a fairly simple approach works reasonably well, and that's sort of reassuring, I think. Sometimes we don't always need super fancy things. Not surprisingly, the meta-analysis you can see is kind of clearly, if the model is correctly specified, it works great. If the model is misspecified, it doesn't work well. And nicely, the causal forest did actually sort of across the board generally had the strongest performance. And again, I think that's because it's targeting this conditional average treatment effect. Oh, I didn't say what our metric of performance is here, because it is a little bit nuanced when we have these conditional average treatment effects. So what we did here, the way we, and actually I'll come back to this individual effects point in a second, it's basically mean square error. So for each person in the data set, we have their known true effect from our data generating process. This is the mean square error of the individual level predictions averaged across people. One thing we've done in our papers is per yesterday's conversation, in the real world, we don't know, we can't estimate individual treatment effects. The way we think about it is patient profiles. So we sort of think about it as what is the predicted effect for someone with this covariate distribution? And sort of we think of it as these individuals as representing a group of people with a particular covariate profile. Okay. So back to the motivating example, so we, given the results, said, okay, we're going to use the causal forest with pooling and this trial indicator approach in this data set. Okay, fine, but so then we get these results. So for each person in our data set, we have a conditional average treatment effect estimate. What do we do with that? So there is a bit of a literature, I'm curious to hear more from Guido, who probably knows more about kind of current thinking, of an idea of what's called an interpretation tree. So we take our Kate estimates, and then we fit some sort of cart-ish tree-based approach, or maybe something a little more complicated, to kind of understand which variables were the ones driving the conditional average treatment effect. So in this case, this is not the prettiest picture, but age, the person's weight, their baseline MADRS score sort of seem to pop up. But age is kind of, in some sense, one of the stronger ones. Okay, so and again, I'm sort of thinking about like how are we kind of communicating this to the people who might be making treatment decisions using these results. So, okay, we can't really, and I mean, I think we as a field should be thinking more how to do this. I'm taking the easy approach for now. Maybe, so it looks like age might be among the more important. So, okay, let's look at the conditional average treatment effects by age. So age on the x-axis, treatment effect estimate on the y-axis, and yeah, if we squint at this, like maybe there's some signal there. Also, one note, again, messy data. You might notice the red, which is one of the studies, they only had age categories. So we only knew that someone was between 25 and 35, 35 and 45. So kind of, so again, messy data. But then I sort of think, okay, well, if we're going back to just a single variable for age, like why did we go through this whole causal forest? Maybe we should just go back to a parametric model and put age in as an interaction term. And that might be like, and actually I was just talking to a friend who works at Novartis, and she was saying that that is sort of how they're often thinking about this, is like the machine learning approaches as like an exploratory data analysis in a sense to see where the signals might be, and then go back and do more confirmatory studies that kind of examine that. Also, though, note here, I didn't put uncertainty bounds around these dots. If we do that, here's the sorted by treatment effect estimate. The gray lines are the individual uncertainty bounds for each person. And again, this is just person by person. We haven't done anything fancy or like conformal or anything, but there's a lot of uncertainty, and like certainly it's not obvious to me that clinically I would want to make different decisions for different people. And in some ways that's like a nice lesson. Like if that's correct, like that's actually an easier treatment recommendation. And I will say, I think partly some of my skepticism in this world is that I work in mental health, where we don't know a ton about mechanisms. There's very little evidence of sort of what might drive conditions. So like cancer, there are some use cases that are like really clear effect heterogeneity based on genetic factors and things. In a lot of other fields, it's just much murkier. And I think this is like typical. Okay, let me turn, so all right, let's say, okay, fine, like, let's pretend actually that there is actually more evidence of effect heterogeneity. Really, the idea of a lot of these approaches is to then say, okay, how do we guide clinical practice? Like really we want sort of, if duloxetine is better for some people, how do we help physicians sort of prescribe in ways that are supported by this data? Okay, but here is my like existential crisis. I mean, not really, but like these are the practical things that come up. When we have future patients coming in, they're not in any of our trials. So remember earlier I said we have to account for trial in when we're combining, but future patients, they don't have a trial indicator in their data set. So this is one where what we've started doing is essentially looking at approaches to integrate across trial. I mean, that is sort of natural, and sort of at a very basic level, essentially what we're doing is just integrating across and sort of accounting for trial, like getting multiple predictions, but across the distribution of trials. And again, most of this is me, just like some of the things I'm struggling with now. I don't know if that's the right thing to do, though. Like a given future patient, maybe they're more similar to people in trial 1 than trial 3. Maybe their context is more similar to trial 1 than trial 3. Maybe we should upweight trial 1. But anyway, I don't think anyone is tackling this yet. If someone is, please let me know. So I'll tell you what we've done so far, but again, I'm sort of signaling some of the sort of remaining things that I think are, that need some attention. So in our case, again, we're basically borrowing, let me actually just go to this picture, borrowing, not surprisingly, from an idea of like overall variance as a function of the sort of within study variance and the across study variance for each person. And so we can get sort of a prediction interval for each person that accounts for both the, again, within study, the vertical bars I showed earlier, and the variability across studies. This is just a little not helpful graphic of that. I want to say, though, and this is maybe for all the meta-analysts in the room, remember, we only have 4 studies. So estimating a between-study variance is very iffy in this case. So I think that is also, I want to acknowledge that. We're doing it, but I want to acknowledge that as well. And I think, honestly, like, this use case is not different from many, many use cases of these sorts of approaches. Okay, we did a simulation here. I'm going to actually skip it because I don't think it's as interesting. So I will just sort of illustrate again, sort of in our case, we ended up using this to predict, and this is where I'm going to start to bring in the EHR data. So in this project, we have the 4 randomized trials, and then we also have electronic health record data from Johns Hopkins and from Duke University Health System. So what we did was we have our results from the 4 trials, and we are going to use the Duke patient population as our sort of target group that we want to predict conditional effects for. Here is just a little bit of data on how the sort of 1,200 trial participants look similar or not to the Duke patients. I haven't told you anything about the Duke patients, but essentially it's individuals with major depressive disorder in the Duke system. That could be a whole talk, though, about sort of defining that cohort, especially in mental health, where people come in and out of systems very frequently. We don't have, like, nice, consistent, you know, the issues of informative sampling that we heard about yesterday are very strong in mental health research. People might be at, like in Baltimore, they might be at Hopkins for 4 visits, and then they might go to University of Maryland, or they might get admitted to the inpatient psych unit at Maryland, and we don't see that in the Hopkins data. So major issues with even just defining a cohort of people that we feel like we have consistent data for. But again, maybe the Q&A, we can come back to that. So, but you can see that other, you know, that sort of age is similar, BMI broadly. There's a little bit of a difference, or actually a big difference on whether individuals have anxiety. And this is, you know, I've done a lot of work on generalizability of trials. This is very, very common because the trials exclude people with comorbid anxiety in this case. But even diabetes, you can see a big difference. I think that actually is, I didn't say this earlier, some of the trials were conducted in Europe and Asia, actually, and so I think some of that BMI, I mean, the diabetes difference. Interestingly, BMI doesn't show as big a difference, but anyway. But so we can see there are differences, but we can, again, we're going to try to predict the effects. And look, the picture looks similar, so not surprising. There's not huge evidence of effect heterogeneity in this case. So if we are sort of predicting effects in the Duke population, looks kind of similar. And again, maybe nicely for clinical practice, actually looks like duloxetine should generally be sort of the preferred treatment. It also is actually substantially cheaper than 4-deoxetine. We did try to sort of tease apart kind of again, like is there a little bit of evidence of sort of for whom 4-deoxetine might be better, or for whom like the choice is more clear, but it's again sort of mush, especially as you can imagine from this sort of plot. Okay, let me just take a few more minutes. And again, sort of my goal here was to just kind of help, and this is a lot of what I do, is sort of like, what do these fancy methods mean in practice, and how do we sort of adapt them, use them well and responsibly for kind of public health medicine especially. And again, I kind of have already talked through many of these things, but I think there's a lot of work needed. I think yesterday at some point there was sort of some talk, might have been during Mihaela's talk about like diagnostics. So I think we need better diagnostics. We need more graphical displays of results, sort of how do we really work on that second step of communicating both what we did to develop trustworthy approaches, and then also how do we sort of communicate the results. So both the process of doing it and then also the results. I think there's, like, I'm not convinced our uncertainty estimates are fully correct, so I think there's also that. And then I just have this also existential crisis in my world, at least, that even when we combine these data sets, it's actually unclear how much effect heterogeneity there really is. And so how do we sort of grapple with using these methods in that kind of context? You know, there are a few cases where there's like clear moderators, but in a lot of science, at least the worlds I work in, it's really not clear. let me take a couple minutes to talk about the electronic health record data. So again, I wrote this grant that was like, oh, we're going to combine the trials and the EHR, and isn't it going to be wonderful? And we knew it was going to be challenging. I will say it has been even more challenging than expected. And one note, one thing that actually has been really good is actually the funder originally was like, well, you can't just use the Duke EHR, you have to get another. So I connected with someone at Hopkins, and we're using the Hopkins as well. And that has been incredibly useful because seeing the differences between data systems has really helped us see problems in the data. Where like when we compare various variables, so there was like fibromyalgia, which is a diagnosis, was like really, really high in Duke and non-Hopkins. And so then we had to sort of dig in to be like, well, what is driving that? And it turns out Duke was actually prescribing these medications for fibromyalgia just as like part of their clinical practice. Another example I referenced to someone is, and again, this is partly through, we have clinical collaborators from both universities. Duke, if someone goes into the emergency department and then is admitted to inpatient psychiatric hospitalization, or actually any inpatient, they have a special code for that. So it gets kind of coded jointly. Whereas at Hopkins, you get like the urban emergency department code, and then you get an inpatient code. If we didn't know that, we easily could have sort of not accounted well for inpatient hospitalizations, because we'd be sort of missing them in Duke, and maybe overcounting them at Hopkins. So things like that, where just kind of there's lots of efforts towards data harmonization in the EHR, but it's still an incredibly messy situation. The other thing that we're really struggling with, although we are starting to make baby steps, is this problem of different outcome measures. So, I mentioned earlier the trials, like their goal is to show a change in depressive symptoms, in 6 weeks, 12 weeks, et cetera. So that's what they measure. And they have small samples, et cetera. EHR is not measuring depression symptoms. I'll say more on that in a second. Just in the basic EHR system, we have information on what treatments people got. We have information on their diagnoses. We don't have measures of symptoms. In the EHR, the outcomes of relevance are things like inpatient hospitalizations, emergency department visits, measures of sort of extreme severity. So my postdoc Harsh Parikh is now working on some stuff to try to articulate, is there any value in combining these? And the answer, not surprisingly, is no. Unless we have validation data with both measures, essentially you have to make incredibly strong assumptions about how the MADRS score relates to inpatient hospitalizations in this data set in order to really benefit from combining them. As one little glimmer of interest and hope, we did get a supplement grant to do natural language processing, essentially, or not LLMs, in the clinical notes. So we are now basically trying to pull out from clinical notes something that we think is going to at least be closer to a depression score. It's still not the MADRS. It's this other CGI score that physicians use, clinical global impressions. But it's also unclear to me if these LLMs are going to work, or do they work in Duke and Hopkins, all the sort of generalizability. So we are exploring that, and I'm excited to be digging into that. Although again, partly even just clinical notes are super messy too. And in fact, our psychiatrist collaborator was like, oh yeah, actually, usually in practice what we do is we just cut and paste. So we use the previous one and we just cut and paste, because we were like, oh, maybe we can look at changes in CGI score over time within patient. And he's like, yeah, maybe, except that 90% of the note is probably going to be the same text, because it's history of the patient, et cetera. And then there might be one sentence that's seems to be doing better, or whatever. So again, I think there's great promise, but also we have to be realistic and sort of think through how to use this data well. So stay tuned. Maybe in a year I can come back to talk about it. So general lessons, again, I don't mean, I'm really not trying to be a downer. I am a huge fan of translating, like really my goal is sort of to help this group think about how do we translate these really wonderful statistical advances and sort of computational advances to have them be useful in medicine, public health related fields. And more, and I'm just like, it's a theme of many of our work, but like fancy methods can also only get us so far, I believe. If we don't have comparable measures, if we don't have, like in my case, if we don't have validation data with the MADRS and the inpatients, like, yeah, we can make some assumptions, et cetera, but like, what are we really kind of tying that to? So again, I'm increasingly want to be sort of thinking about how do we have methods that are transparent, replicable, and with diagnostics. And sadly, those are the things that are not always well recognized by our field, but I hope that we can continue to push on that. In this room, I don't need to say, remember the fundamental problem of causal inference. And then I just have to always use this little meme from when that big, what was it? Whatever it was called, was stuck. So that is it. This is just a few resources, especially if you want to kind of get a sense of the lay of the land. So Julie yesterday mentioned the Colnay paper, which is a really nice review, and then a few other sort of reviews of these sorts of approaches. And thanks to PCORI and NIMH for funding. And yeah, happy to take questions.
Hi, Liz. Thank you so much. I'm Michele from NYU, Santa Caterina. I always forget putting my last name. Fantastic talk, very excited. One of the big challenges that I see even from an applied point of view, when I work with data integration, is that randomized trials have multiple, very strict inclusion and exclusion criteria. And real-world data or external data are just like whatever. So structurally speaking, the probability of study participation given feature is violated.
Yep.
So one way to overcome this is go fully parametric, extrapolate, which I don't like, or I don't know. So do you have any thoughts on that? Thank you.
Yeah, I mean, I have thoughts, but not solutions. I totally agree. And I mean, this is where some of the cross-design synthesis approaches can be useful in that you can sort of see if you can see in the EHR, for example, who would have been eligible for the trial, and then use that to calibrate sort of the extent of unmeasured confounding in a sense, and then use that to sort of back out. It's like, okay, do we see a similar effect estimate in those? And then you can use that to sort of adjust the effect estimate for the people who were excluded, if that makes sense. So Ellie Kaiser at Ohio State has done some of this. Like if you have a 2x2 table, I'm not describing it well, but you can kind of estimate the unobserved confounding essentially using the overlapping group. This is though also I think a tension where, and actually Harsh Preek, the postdoc I mentioned, who comes from computer science, it's been really, really great to like bring these worlds together. The other thing I'm interested in is what matters, of course, like overlap only matters if it's lack of overlap on effect moderators in this context. And so I actually think, and actually Ivan Diaz and Kara Rudolph have done some work on this of like, how do we measure overlap in a way that also examines moderation? Because in some ways you don't want people to over worry, because there might not be overlap, but if it's on a variable that doesn't matter, like then we don't need to worry. But Harsh is working also on some stuff, actually with Avi Feller at Berkeley, on like how much extrapolation is okay, and because like age, easy, like yeah, probably we feel okay generalizing to someone who's 67 beyond if 65 was a cutoff, but like at some point we're no longer comfortable with that. So I think formalizing those sorts of things or sensitivity analyses where we could sort of say, how different are those people that were excluded? I think those are some of the approaches to try.
thank you also very much for taking this practical perspective to it as well. I appreciate it. I'm Mats Stensrud and I'm from EPFL. I just want to follow up on Michele's question. And since you mentioned design on the last slide, so where do you think the way go forward for doing designs? Because in the way you're talking now, it seems to me that recruiting trial participants from an existing cohort seems like a very nice way of addressing this, right? To have positivity and also see whether there are effect modifiers outside of the trial eligible population.
Yes, totally agree. Like in cases where we can have a well-defined, I mean, actually step one for all of this is usually what is the population of interest and being clear. And yeah, if we can then do like sometimes they're called patient preference trials, or where you sort of let people, some people are in the trial, others are in a kind of companion cohort study where it's the same data collection. Those can be really, really useful for this kind of thing.
And that's related to what you said, that you often don't find heterogeneity in effects, but that could also just be because of the inclusion criteria to the trial.
It could be exactly inclusion. And right, actually, thank you for saying that, because the trialists, remember, their incentive is to show a big effect estimate, which they are more likely to do with less heterogeneity.
Yes,
and
exactly.
so they want a homogeneous population with large effects.
No wonder why they don't want to have anxiety patients in the same cohort.
Yeah, yeah. So, and maybe that makes sense for efficacy. Like maybe that is the right thing to do, but then we need to be careful about the conclusions we draw from it.
My name is Martin Huber from the University of Freiburg. Thanks a lot, Liz, for this interesting talk. I just wanted to mention another aspect this can be useful for. So it's not only about, maybe not only about estimating effect heterogeneity in experiments, but actually if you really do find that all the effects conditional on X are homogeneous, right? That actually tells you that if you have in an observational data that the exchangeability or the selection on observers assumption is satisfied, you should find exactly the same effect in observational data, because there are no moderators anymore that are unobserved, right?
Yep, yep.
And so you could construct tests based on this for identifiability and observational data. Is this something you have thought about?
I have not like really thought about it, and I'm trying to remember. I feel like there might be a paper or two that does that. Maybe Martin, Borsch something at Michigan. Anyway, like.
Okay.
Yeah. No,
it's also in the computer science literature. They call this stability, right? So what they think about different randomized trials as different environments, and then they say like, okay, you think of it like being an instrument, right? So if you go from one trial to another, it's a different value of the instrument, but if actually the effects do not depend on that value, right?
Right. Yep.
Then you're saying, okay, your causal environment is stable, and that means you should find the same kind of effect in observational studies. If you don't, then you don't have actually the selection on observers assumption satisfied. So I think that's a very promising way to go with these experiments.
Yep, agreed.
Thanks for the very nice talk. Really enjoyed it. I also really appreciated the discussion of the challenges of interpreting treatment heterogeneity estimates. Like, you fit a Kate model, it seems pretty good. Now what? I've obviously also had a lot of experiences of that type. Maybe the most extreme ones were Susan Athey and I, for many years, taught this applied class on causal inference with a machine learning focus. And then there's the last day of the class, it's student presentations. And then it's like 5 minutes, bam, bam, bam. Students are showing these findings of treatment heterogeneity. We had very strong incentives to figure out, like, what do we tell the students? So what do you need to show us so we believe, you? So if it's okay, I thought I'd share kind of something we found helpful. I'm also curious to get your perspective on that. First, on that interpretation, like how does treatment heterogeneity align with age, like you mentioned, or something like that? One tool we found very helpful is kind of estimating best linear projections of the Kate function. So the thought experiment is that you would want to run a Kate regression where the Kate is on the left-hand side variable and you predict it from other stuff. And then algorithmically you can do this if you put the double robust scores on the left-hand side and run that regression. And what at least I find nice is that it gives a unified framework for doing everything. Like you get the Kate in a non-parametric way and control for confounding in a non-parametric way, but then get linear summaries.
Yep.
The other thing we found very helpful for validation is different rank-based measures. I know Kosuke has also worked on this in the case of like Gini curves. So the idea is that if you go on a test set, then if you find that here 10% of people who you claim respond the most, well, do they actually respond more than the others? And then you can sweep that threshold and get different area under the curve measures.
Yep.
So anyways, these are two things that we found if we had, as students showed us, then we had an easier time believing them. I'm curious if you've tried any of these methods or have any experience.
You're like, I should have, we have actually. I don't have them in the talk, but yeah, exactly. And I think probably seeing some examples of yours. Yeah, I'm trying to, anyway, short answer is yes. I mean, kind of similar substantive results as what I showed here, not surprisingly. But yeah, I think those sorts of things and the, oh my gosh, sorry, I'm not gonna be helpful right now because there was like a metric. We were also trying to compare, anyway, but yes, we actually have both of those, I think in the paper itself.
Thank you so much for such a thought-provoking talk. Four questions. One of them is, while we like causal forest, we know that in machine learning, in many scenarios, there are much better methods than that. So have you tried other machine learning methods than that? There are many available. That's the first question. And maybe the performance and the improvement would be much better. Number two, on the issue of interpretability, there are nowadays papers on trying to look at, for any black box model, try to understand predictive and prognostic methods for determining the variables that led to that, which would allow you to interpret. And maybe age is not the important variable, but other variables are. And these methods could be applied post hoc on top of any black box model.
Yeah.
On the issue of uncertainty, again, there are many methods nowadays for both aleatoric uncertainty, which I think is interesting, so as well as epistemic uncertainty, whether it is conformal prediction or other methods. But looking at both the epistemic as well as the aleatoric, would that be a solution given the existence of these methods? And finally, a thought, I'd be curious about your thought on it. One way in which we use this information to look at prospective patients after you did this analysis is by combining ideas from synthetic control with ideas from machine learning, where we try really to find approximations of the patients that you have in front of you on the basis of data that exist from these other clinical trials. And so maybe not directly synthetic control, but variations on synthetic control. So sorry for the many questions, but the talk was...
Yeah, no, that's great, and this is why it's like nice to have you here to bridge worlds. We haven't, I mean, please send me sites if there's specific newer ML methods to try, like happy to try them. Again, I guess I'm a little skeptical. I think in this data, like from all of the investigations we've done, I'm pretty skeptical there's not signal there, and I actually in some ways might worry if something like, but yes, I mean, it's worth seeing. The interpretable AI, it's a great point, and actually Harsh, my postdoc I mentioned, worked with Cynthia Rudin at Duke, and he's really an expert in that. So yeah, I could also ask him for sort of recommendations here. Anyway, we should follow up, or like, I would love references and such, and this is again why. And most of my interest, again, is like, is that sort of helping people think through, like when a new method comes up, how does it fit within, and is it sort of gonna be, you know, is it kind of worth the, you know, and under what cases is it gonna sort of bring new methods? And I think we also have to be realistic about kind of the practicalities of like implementing. But yes. Oh, yeah, so I have a student right now who's going to be trying to do conformal with this, but she's just digging into it. So yeah, that's very much next on our list.
Thank you. Anna Gottard, University of Florence. So I had another comment on the use of the tree for the I'm really against, and I'm telling you why. So imagine the algorithm as a data generating process, okay? So there are some variables like age, which is continuous, it's always coming age, gender, which have many paths through the prediction, okay? Descartes used a greedy algorithm that is looking for marginal association. So the many paths you have, the most probably you are taken for first, and so you will appear as to be the most important variable, while you will not be. So probably age is not your...
No, it actually is in this case. Like, so I'm only showing like some of the diagnostics, but we did the linear projections. We also, oh my gosh, I was just thinking of something else. We did, anyway, like in this case, it actually is. And again, it's pretty weak too. But in terms of, so yes, this was like just a little example, but we have done other sorts of things. Yeah, understood. Actually, can I say one more? Sorry, I don't mean to interrupt. But I think this is exactly why we also need people in this room writing papers that help like the rest of the world know how to use things well. I guess that's like, again, if I have like one goal is sort of the like there's so much knowledge that doesn't get sort of, so like doing like great tools for graphics and things like that is really important. So, sorry.
Very nice talk, really enjoyed it. So one of the things you do is take these 4 trials and then kind of use that to predict what would happen for the Duke patients. You could also take one of those 4 trials and put it aside, use the other 3 to see how well you do, and then actually compare to the results from that trial and kind of see whether without the covariates you actually predict the results well, or once you have the covariates you predict things well, and whether you really need to do the 4th trial, or whether you could have made the right decisions based on the 3 trials. Yeah. So that's one comment. One more comment. In the end, you don't find a huge amount of heterogeneity in terms of the treatment effects, but you could also look at the conditional average treatment effect and just look at the 2 components, the conditional mean of Y1 and the conditional mean of Y0. There's probably much more heterogeneity there, but if it were the case that even there you don't find much heterogeneity between the locations, between the trials, that would actually be much stronger evidence that the heterogeneity of these trials doesn't actually matter all that much. And so that would be very helpful to look at.
Yeah, thanks. And I think that to me, like partly, and also Martin's comment earlier, the sort of number of ways integrating data can be used, like that's another, like in some ways that's a whole other category, an additional category of like using it to probe assumptions essentially, or sort of to understand. And I think this is partly, again, like right now, a lot of these fields, and even the papers, they aren't super precise about what the goal of combining the data is. And so it's sort of, I think we'll all be better off if it's sort of much clearer, like what is the goal here? Because there's a lot of potential uses. That's a great example.
Yeah, thanks. Yes, it's always, she was my TF, so it's always good to learn from you. So I started sort of getting interested in this heterogeneous treatment effect thing, and it seems the goal, at least from scientific point of view, is to find some relationship between covariates and treatment effect that are robust to across different environments and different populations. I guess that's the Martin's point. And of course, the threat is that always unmeasured confounding across different populations. And I guess you mentioned also like different outcomes, but that could be also thought of it as if they're trying to measure something similar, it's sort of the slightly different measures of the same thing, but like there's some confounding. So I'm just curious as like if you've seen any good approach that would address this random confounding across, different populations, even though maybe the treatment effect is reasonably well identified within each study. I'm just curious, you've seen the broader array of methods. So,
I mean, I guess is another way of asking your question of sort of the disentangling the individual level factors that might drive effect heterogeneity from sort of system or setting factors in a sense.
Yeah, it seems like there's some scientific theory that indicates each type of people should have,
yeah.
not an effect or the end of that. And that's what we sort of want to find. I think
Yep.
different populations.
Yeah.
They don't really have a specific target population
Yeah.
per se.
Yeah.
but
There's like an
find
innate
something
understanding.
that
Yeah.
really, the loss to different
Yep.
environment, different populations. That seems the ultimate goal.
I think that's right. And in some ways, one thing I've actually been thinking about is can we use this, and maybe relates to Guido's point, the variation across trials in part as an indication of how robust, how safe we are in sort of, because if there's huge variation, and I think the meta-analysis world does this to some, if the random effect in a typical parametric meta-analysis is big, that's sort of a sign that, there's something else going on here, and that we don't really trust the stability of our results. So I think there's pieces of that. I don't offhand, I don't know of a specific thing that's doing that explicitly, but it's sort of underlying a lot of this. While we're moving the microphone, I will also add, part of my interest in all of this, just to motivate this, is sort of the National Institute of Mental Health requires every randomized trial to do moderation and mediation analysis. And so I should have said that up front. Remember what I said? We don't know great. They want that, I think, because they don't really understand the mechanisms of action of many of these medications. They sort of know they work. And so then they kind of want to do mediation and moderation to try to understand what you're saying. Is there some biological thing? But part of my point here is for that world, honestly, to sort of understand the limits of what we really kind of, because they have these sort of grand plans that I'm not sure are realistic.
Someone there should be waiting. Yes.
Thank you for a great talk. One comment first is really a plug for the Society for Research Synthesis Methodology, because all of what you're talking about are methods for evidence synthesis.
Yes.
And so they have a journal, Research Synthesis Methods, that in the past was not really causal, but there have been a lot of people who have gotten from causal inference who have joined, and I would encourage all of you, if you want to publish articles on this type of stuff, that's a really good place to go. My question then is, really what you said you didn't want to talk about at the beginning was you're leaving out the non-adherence. And so the randomized trials are, in health anyway, are intention to treat.
Yeah.
In other things, in computers and Google stuff, you don't have problems with adherence.
Yep.
So, and the observational studies are about the actual treatment effect. So how do you try to combine them? Do you try and get, how do you get those estimates to try and estimate the same estimate?
Yeah, this is something I've struggled with. And actually, the observational study isn't even estimating the effect of actually taking. It's estimating the effect of having a prescription in the system. So, yeah, I don't know how to deal with any of that. And so I think it gets also back to the clarity around the estimand and sort of the and actually Peter Steiner and Vivian Wang have a nice paper about focus on sort of replication studies, but where they kind of detail all of the different reasons, why it's hard to compare an RCT with an observational study and this sort of thing, that what is the estimand you want to compare. We have sort of struggled with that here too, and this tension of with the EHR, partly we want a subset, for one purpose, we want a subset to people who look like the trials so that we can understand confounding and such. But then we also don't want to do that because we want the representativeness of the trial. And I mean, you can do two analyses, but anyway, it's things like that where it can be quite nuanced. So I agree.
We're going to take two more questions. I see Andrea, and then there's someone in the back.
So thanks a lot. So in your slide, you had a bullet on the future. And this is perhaps related also to other questions, but my prior is that in order to say something about the future based on any kind of study we do, we need some kind of homogeneity, stability assumption. Do you have in mind something more than that? Is there any new things that, or we are still at that point? Because that's crucial, no?
Yeah, no, I agree, and it's often, I would love if anyone in this room is doing stuff on this, because actually, yeah, I mean, we are always extrapolating into the future, by definition. Beth Ann Griffin, who's somewhere, and I have a proposal where to sort of start investigating time and sort of thinking about like how do we do this a little bit more formally and sort of understand stability over time as a way to help us understand whether things might generalize. Perfect. Perfect. That's what I was hoping someone in the room would say. Awesome. I will look for that. So yeah, because I think right to this point there hasn't been like a formal structure for thinking about it, but it's really, really important.
So I just want to point out one more aspect. So Kosuke, and you mentioned we want to understand heterogeneous effects to transport across populations, but you might also be interested just in maybe a very complicated rule in your own population, and that's it, right? So there's an example from a health service at Causality where they found a pretty complicated XGBoost rule for hepatitis C. They couldn't distill it into anything interpretable, but they just ran with the rule and found out a lot of people who should be invited. So that's like a different, maybe orthogonal motivation for these kind of things.
Yeah, cool, thank you.
Okay, well, first of all, I want to thank you, Liz, for the amazing job. All right, we are going to get started. Welcome back. All right, thank you. Thank you for coming back. Thank you. Well, welcome to the next session. We are going to have a lovely panel session. First of all, I wanted to introduce a very special guest of the conference, the fan. So,
welcome.
Welcome. Thank you for coming. All right, so it's really my pleasure to introduce it. It's a really incredible panel. We are going to talk about environmental health policy and climate change. This is how it's going to work. I'm going to briefly introduce the three speakers. They're going to provide some comments, and then we're just going to open up for a panel discussion and question and answer. So it's really with great pleasure that I want to welcome Marshall Burke. Marshall is an associate professor at the Doerr School of Sustainability at Stanford. He's also deputy director of the Center on Food Security and Environment, and also is a principal investigator of environmental change and human outcomes lab. It's been really a pleasure for me to interact with Marshall over the years. You will learn his lot of experience in, he's an economist by training, and a lot of experience in causal inference in terms of attribution, a lot of interest in working on wildfires, exposure estimation, and the impact of wildfires on behavior and health outcomes. You all have learned about Elizabeth Stewart. I'm not going to introduce you again. And then we have Corey Ziegler, is a professor of biostatistics, recently moved to Department of Biostatistics at the Brown School of Public Health. Corey has the responsibility of putting, really getting me into the causal inference world. Yeah, I'm just gonna blush.
Is that good or bad?
I don't know. I still figure. Last night at the dinner was a really good thing. So, no, I'm really grateful. He is doing really fantastic work on really thinking about foundational issue of propensity score and Bayesian causal inference, and also propagation, uncertainty propagation in the design, in the design phase of causal inference into the analysis, thinking about principal stratification and many more things. So I'll be quiet, and then I'm just going to turn it to, I think we're going to go this way, Marshall, Liz, and Corey, and then we will open up for discussion.
Great. You guys hear me? I talk pretty loud. I'm going to not lean down. Thanks, Francesca. Great to be here. So Marshall Burke, Stanford. I am an economist. I am here today to talk about climate change, causal inference questions related to climate change. I want to try to cover both the climate science and more of the economics of climate change. I think there aren't climate scientists in the crowd, which is good for me. I'm not one either. I'll try to do it justice. Briefly do it justice, and then show you some of our own work, which you will hopefully help me do justice to as well. I have want to pose some open questions and challenges as I'll show you. So let me start. I can advance these. There we go. This guy's not working. Oh, now it is. Okay. This question is often framed in terms of causes of effects, so we made that distinction yesterday. Here it's framed slightly differently, but let's think about it in the causes of effects. So global warming is observed. We can read that off thermometers. We know that it's happening, so we don't need to argue about that. What is the cause of global warming? So the causes of effects question. So let me start with the climate science here. Question number one, causal question number one, do increasing greenhouse gases cause global warming? Or framed differently, are humans the cause of global warming? Okay, basic fundamental science question. Who generally, let's show of hands, who generally would agree that humans are the main cause of global warming? Okay, pretty much everybody. This is Europe. What is... Okay, who would be comfortable articulating what the causal underpinning of that claim is? Climate models, something, right? Okay, so what is the causal underpinning? We can think about using statistical causal inference. A lot of the approaches we have seen so far, using this approach or these approaches is a challenge in this setting for one main reason. So if we want to understand the impact of emissions on climate outcomes, say global mean surface temperature is one we focus on a lot. A real challenge here is that emissions are pretty smooth in time. So if you can see this green line, this is total fossil fuel emissions over time back to the 1850s as best we can estimate. They're pretty smooth. There's some jumps, and so maybe you could think about exploiting some of these shocks, these variations. But a problem is that CO2 is well mixed in the atmosphere. It doesn't matter where you emit it. It sticks around for a long time, and it gets mixed in the atmosphere. The residence time is centuries, so it doesn't just cause warming in the year that it's emitted. It causes warming for the next 100 years, to our best estimate. And so that makes identification challenging. You have one time series and an X variable that sticks around for literally centuries. So this has not been using statistical causal inference tools, at least as we have practiced them so far at this workshop, has not been the standard approach. Instead, we've done other things. First thing, we have done very early experiments. So scientists were interested in what they called in the 1850s carbonic acid. So here's an early experiment from 1856. Eunice Foote here, shown, I guess, with her dog, puts carbonic acid in a jar and normal air in another jar and exposes them to sunlight and then measures the temperature over time and discovers, okay, the one with CO2 gas warms up more quickly. It traps Earth's radiation. This was, again, in the late 1800s. This was pretty well understood by Arrhenius and other scholars. So in some sense, the basic physics and chemistry of the greenhouse gas effect has been understood since the mid-1800s. But really, the inference we do is built on physics models that, again, are built on these basic understanding of physics and chemistry that date back for over a century. So the way these work, and these have gotten more and more complicated over time. These have been built since about the 1960s. in various forms. You divide up the atmosphere and the ocean into little blocks, and you write down the physics that determines how things move within the blocks and between the blocks, right? Again, guided by the basic understanding from Arrhenius and Eunice Booker. Okay, once we think we have a good physical model of the world, then what we do is we run it with different, what climate scientists call forcing. So greenhouse gas is a forcing, so you can run it with and without human emitted greenhouse gases. And basically, what climate science tells us is the only way to reproduce the amount of, so the y-axis is cut off here, this is warming, global mean surface temperature warming. The only way to get the world to warm up as much as we've observed in the models is to feed it the greenhouse gas emissions that we have emitted. If you don't feed it the greenhouse gas emissions, you just give it volcanoes, you just give it the natural emissions, non-human greenhouse gas emissions, temperatures are roughly stable. So this is the main tool for causal inference. These are all the IPCC claims on, or most of them, on why humans or whether humans are causing greenhouse gases are built on basically these model experiments. Some other data as well, but this is the main line of evidence. Okay, what are some worries here? We do a lot of calibration in these models. Maybe we just calibrated somehow to the time series, and the models then can reproduce the time series well. One thing we can do with these models, because they have been around for a while, so Manabe won the Nobel Prize in Physics for his work in the 1960s, building these first mathematical models. Because they're so old, we can actually look at predictions from the 1960s, feed them these models' emissions that we've seen from the 60s, and compare what the predicted warming from these models was in the 1960s versus what we actually observed. So one way to actually predict these out of sample, because we've been running this uncontrolled emissions experiment for the last 50 years. And it turns out these models do pretty darn well. There's been a lot of development since, but even the models, the really early models in the 1960s, pretty much nailed the subsequent warming over the next 50 years. So out of sample, it looks like these models, again, built 50 years ago, perform pretty well on emissions data over the next 50 years. Okay. This is a paper that does this for a bunch of different models back in the 60s and 70s to show that, so the blue is what's actually observed, the red is the model prediction, and you can see that those things are pretty close. Okay, so maybe we're convinced, we understand the physics pretty well, at least at broad scale, these models are making good predictions. Here's another thing we want to do in climate science. So I took, this is from a July 2021, maybe many of you, or some of you might have experienced this event. There was a huge flooding event in Germany and Belgium a few years back. There was another one in Central Europe. A big question in climate science is to what extent are these specific extreme events influenced by a changing climate? These are very destructive events. They kill a lot of people. They cause a lot of damage. And so a causal question is, what role did climate change play in the likelihood of these events? A lot of these events are outliers, so you can see here's the time series of daily precipitation in Germany, near where this flood occurred, and the red dot is the July 2021 event, right? So a real outlier in the historical time series, very disruptive. Okay, there is a small cottage industry of science who scientists who right after when these events happen come out with, and literally within days, or in this case a month, estimates of how much that event, that specific event, individual event, was influenced by climate change, or how did climate change the probability of that event, which again is a causal question. It's interesting scientifically, I think, so did climate change make these events worse? It has also become very important legally. These claims have formed part of the foundation of trials that are happening in the EU and the US around the country, around the world, where individuals are trying to hold fossil fuel emitting companies responsible for these events, right? And the logical argument is manyfold, but depend at least in part on the scientific claims made here, that these events were made worse by a changing climate. Okay, so how do we actually make that causal claim? How do scientists make that claim? They do it in two ways. Here they actually use statistics, so what they're going to do is take this time series, or time series like it for other events, and they are going to fit some sort of distribution to it, typically some extreme value distribution, and allow key parameters in that distribution to change over time as a function of, in this case, mean temperature. It could be CO2 in the atmosphere, mean temperature. They appear to give roughly the same answer. You get those distributions as a function of t, and then you can ask, how did a warming temperature change the probability of that event? How did it change the return interval? So here's the plot they got for the 2021 study. The blue is the historical return interval. The y-axis here is the extreme, how much rainfall you got on that given day, extreme one-day rainfall. X-axis is in log, it's the return period. And basically you take the ratio of those return periods, and that tells you, by this estimation, that this is where the claims come from, how much more likely climate change made that event. You can also use climate models to do the same question. Again, you run the same sort of experiment. You run the climate models with the greenhouse gases, without greenhouse gases, and you try to calculate, okay, how often in the climate models do I see the sort of rainfall event that we saw in 2021 with and without those forcings. It turns out in this setting, so here's the 9 times higher estimate from the observational, from the statistical extreme value estimates. The models here give you about 2x, so you see substantial model disagreement with the sort of observational estimate. But both of these suggest that climate change made these events more likely. So these are the causal claims. This is sort of the basis of the causal claims. This is not the work I do, so I don't, this work's very influential. I don't want to overly defend it, but this is sort of how influential causal claims are made in climate science. Okay, let me move on to question number 2. Does warming have negative societal impacts? This is a question I work on and many others work on. It's gotten a lot of scientific interest. Some of the challenges here are common to other things that we've looked at. So one is experiments are often unethical. If you want to understand the impact of heat on mortality, it's unethical to put people in a really hot room and see if they die. So we don't do that. We have to use observations. Our physical models are pretty bad. We don't have great physical models of people, structural models of society. We don't tend to take these too seriously. And finally, if we are in the world of observational data, we're in a sort of specific world. So here treatments are often continuous, almost always continuous, and effects are often very nonlinear. And so I think here's a setting in which we don't have a lot of guidance from the existing literature for a couple of applications that we're interested in, but where I think a lot of folks in the room could contribute a lot. Or maybe they already have papers up on arXiv that do this correctly. Okay, so let me just walk you through a quick example. I have a couple more minutes? Yeah, okay. So again, extreme heat and mortality. We've known for a long time, or suspected for a long time, that hot temperatures increase morbidity and mortality, cold temperatures as well. So typically the way we try to estimate this is with panel data. So imagine you observe, and often it's aggregated panel data, unless you're Francesca, who has better data. For me, it's often county level or district level mortality data, and I see those districts over a lot of years, so often we have decades of data. And basically I want to learn or estimate some relationship between mortality and a function of a range of climate variables. Let's think of here just daily temperature. That could be daily temperature today. Importantly, lagged effects are often important to estimate. So today and yesterday's temperature, a range of controls, and here we can think about the standard two-way fixed effects or variants of this that control for time and unit FE, and also other climate variables that might be correlated. Precipitation is one you have to think about a lot in that setting. Okay, so pretty vanilla panel setup here. Where does variation come from in this setting? So we're using effectively within county, within unit variation over time. We tend to think whether this year was hot or cold, or this day was hot or cold relative to yesterday is at least somewhat random if we've taken out the long-term time trend of climate change. And so we think that we've isolated, or studies argue that they've isolated plausibly random variation in T here, and so we're estimating causal effects. Okay, when you do this in the US, when you do this in EU, you get a sort of characteristic U-shaped relationship. So x-axis is temperature, y-axis is mortality, log mortality. You can estimate this any way you want. You get basically the same answer, this U-shaped relationship where hot temperatures kill people and cold temperatures kill people. And there's a bliss point around 15 to 20 degrees Celsius where mortality is at its lowest. Okay. Some challenges here. What are we actually estimating? So again, in the sort of standard two-way FE, this has a bad name now in applied economics and econometrics. And there, in the binary treatment setting, I think we have very crisp statements about what we're actually estimating when we estimate a two-way FE model. With a continuous treatment and nonlinear effects, I think that statement is much less crisp, right? So we think of this as some sort of unit weighted average where the weights are some function of the variance in x between units, but my read of the literature is we don't yet have a crisp understanding of exactly what we're estimating. Other challenges here are two. How do we choose the right set of time controls? What you typically see in these papers is people just sort of try different things and hope it's robust, report it if it is. And then how do you choose this function, right? How do you choose the sort of right function that maps, in this case, temperature to y? That matters because we do some really heroic things with these functions. We run the world forward using these functions to say, how much is future warming going to affect mortality, right? And so getting the function, the shape of the function right is really important for us. Why that's hard, or at least one reason that's hard, is the within r squared here, the sort of amount of variation within unit variation in mortality explained by temperature is really low, right? Like less than 1%. Overall r squared is high because we have a lot of FE, they're doing a lot of work, but the within r squared, right, temperature just is a significant predictor, but it's not explaining a lot of the variation. So we're in a very low r squared, a somewhat noisy environment. Okay, last couple slides. The other thing we want to do, we want to take that response function and we want to understand heterogeneity, right? Who is most harmed? To whom should we target interventions? Is it just old people being affected, right? So again, standard heterogeneous treatment effect questions. But again, we're in a setting where I think the literature does not yet have a lot of guidance for us, right? Continuous treatments, nonlinear effects on exactly how to do this. Again, please correct me if I'm wrong, and there's a quick book. The other thing we're interested in is, are these effects changing over time? So that's another time heterogeneity, which was mentioned, I think, by Liz in the last session. Let me just show you the time heterogeneity. Again, this is important because we're using these functions to then heroically run the world forward and run these simulations of how many extra people die under 2 degrees of warming or 3 degrees of warming. So one thing you might be interested in is, okay, do we already see changing effects over time, right? Heterogeneity by time. We have a working paper on this looking at mortality and a bunch of other relationships. Sorry this is so blurry. I'm going to walk you through, starting in the 1970s, re-estimate this function decade by decade to sort of understand heterogeneity by time. We might think of this as adaptation. If you think of societies are adapting to climate, this thing should flatten out over time, intuitively. And that's mainly not what we see. So we can do this in Europe, we can do this in the US, and you see this thing being pretty stable. Again, this is a very sort of traditional way of estimating heterogeneity. We're just interacting the function here with time dummies. There's probably better ways to do this. Please tell me what they are. Let me finish here, since I'm already over time. We can do this by age group. It turns out it's not just old people who, where we see excess mortality at really high temperatures. It's also under 65s. It turns out temperature affects mortality in lots of different ways. You see more car crashes, you see more homicide, you see more suicide, and those affect, not just old people. And finally, just a plug here, again on the adaptation side, if you're interested in this, please talk to me. We've had a lot of work on mitigation. So mitigation is reducing emissions. Adaptation is adapting to the impacts that those emissions are going to have. There's nice now meta-analyses in economics and other fields looking at various investments in mitigation where we know a lot about their impacts. We know a lot about the sort of impact per dollar spent. We just are pretty well informed on mitigation options. The challenges there are mainly political, not a lack of understanding of what to do. On adaptation, we do not know that at all. We're going to get 2 to 3 degrees Celsius of warming, and we have no cookbook at all for what works. Not only who's going to be most impacted in most settings, as I just showed you in mortality, we don't have a crisp answer to that, much less what interventions actually work to sort of break the link between these exposures and outcomes. So for me, this is a big empirical challenge, and talk to me if you want to help. Thanks.
Great. Okay, I'm back. But this time, totally, actually there are some connections between the two talks, but I'm kind of putting on a very different hat right now. And it's funny, Corey yesterday was like, oh, Liz, you've become really the causality person in environmental exposure. And I was like, no, I haven't. So this is a bit of a story of a statistician who knows causal inference getting pulled into this area, and I'll tell you sort of why. But I am not a climate scientist, et cetera. So I'll talk more about that. Okay, so yes, almost all my work is causal inference. Almost none of it is in what I'm about to talk about. But basically, a few years ago, I got pulled into this National Academies committee, which let me go to the next slide. This is the title, Advancing the Framework for Assessing Causality of Health and Welfare Effects to Inform next Reviews. Okay, I knew none of this before the committee, and so I ended up co-chairing this panel, which I'll say more about in a second. But my goal today is to kind of convey a little bit of what I learned from doing this process, and I think lessons for us as sort of causal inference statistician types. So Corey actually, and maybe Francesca, has sat on some of these committees, so on the EPA. So correct me if I get anything wrong. So in the US, the Environmental Protection Agency, EPA, has the NAAQS, the National Ambient Air Quality Standards. And they have a whole process. And what the NAAQS are is they are sort of documenting levels of pollutants that are acceptable. And so they'll take a particular pollutant, PM 2.5. PM 2.5. Well, yeah, sort of have like a certain level, and they establish like part of there's a whole political process, but part of that process starts with a review of the scientific literature of whether there is a causal link between like pollutant X and outcome Y. A couple points, so health and welfare. So again, actually let me take another step back. There's a causality framework, the preamble to this. There's this integrated science assessment, which is sort of this whole process of assembling the evidence. And there is this piece that lays out sort of thinking about how to assess the evidence in order to sort of establish whether there is a causal link between pollutant X and outcome Y. And just outcomes might be what are known as health, so mortality, et cetera, or, quote, welfare, which is a weird term to use, but it also means things like environmental or sort of like land, like effects on the land or things like that. So our committee was tasked with basically assessing that framework. So our committee was not about examining specific studies and coming up with the sort of this ISA. Our job was to say, how is EPA thinking about causality, and how are they assessing the evidence, and is that a reasonable approach? Tiny bit, so again, I was totally new to this field. So I, luckily though, had a co-chair, Ted Russell from Georgia Tech, who was much more from this area, and then you can see the other members of the committee, including Francesca. A couple notes. I will try to sort of summarize key points. Again, this is one example of the National Academies process in general, where the idea is like government agencies hire the academies basically to come out with these sort of reports, with really the goal of assembling a group of experts from a variety of expertise. And I'll come back to this, but you can see here, well, you don't know these people, but it's a combination of statisticians, but also climate experts, some sort of who focus more on health, some who focus more on, quote, welfare, but really a variety of different pieces of expertise coming together. There's always a very official statement of task for these sorts of reports, so here was the official statement of task. And again, it's a little bit formal language, but EPA requested consideration of frameworks for integrating, documenting, and evaluating scientific evidence to assess causality and health and welfare effects. Bit more context for this. Partly this, and we might come back to this later, this field, as you can imagine, is a very controversial kind of highly combative field. And so in part, EPA had been sort of getting criticized for some of their processes. And so the idea was they wanted this group of outside people to sort of come in and give them advice and say, well, are what you're doing now reasonable, or should you be sort of tweaking things? I'm not going to get into full details of this, but you can see some of the questions. So basically, describe and assess available methods and frameworks. One additional bit of context is these ISAs come up with sort of, in some sense, levels of evidence, so kind of like conclusive, medium, et cetera, and they have like categories. So part of our task was even just saying, like, are the categories appropriate? But then also, new advances, like are there new advances for integrating and evaluating scientific evidence to inform these determinations? So again, EPA has been doing this for many years. They wanted assessment of sort of like, are there ways for scouring the literature appropriate? Are there newer ways they should sort of find research that might inform a given determination? In general, they also take what's called a weight of evidence approach, and this is common across many fields. And I'll say more about this, but sort of they were interested in, like, is that appropriate? Or, should they be doing something else? And I'll come back to that. And then the third, interestingly, I sort of signed on for this thinking, okay, yeah, I know causal inference, I know non-experimental studies, I can help them think about, like, individual, like, things to look at, like, okay, did they adjust for confounders well? If they're using interrupted time series, did they use, and that was not, in the end, really what we dug into, because it was really a sort of higher level set of conversations about combining evidence, synthesizing evidence at a sort of higher level. They weren't even quite ready to, like, getting into sort of the weeds of how do you assess individual studies sort of wasn't really the scope for this report, but it definitely informed some of what we did. Okay, so again, I'm not going to go through this, but I basically said all this, but want to highlight the middle bullet, which again, partly what we were doing was thinking about how EPA currently does this process and this sort of weight of evidence, but then also comparing to other groups that do similar things in a variety of fields, and are there lessons to be learned from those? So in part, I got really interested in it, and I'm glad there's like research synthesis people here, because for me, it has really ignited a broader interest in research synthesis and how do we sort of bring pieces together, which I'll come back to. So one of the things that I was, again, so the process, I haven't really laid it out, but the process is that they kind of collect a whole bunch of studies, and then they summarize them, and then a bunch of experts sit around and sort of decide, like, is there sort of evidence here of a causal link between X and Y? And one of the things that I was happy was a key conclusion of the report, kind of relates to conversations yesterday, is that basically in this context, no single study is going to be like the definitive answer. And so partly, but even just saying that, I think was useful to EPA, because they sort of, some people in the field had this idea like, oh, we can just do this one magical study with this data and like get the answer. But in this context, like that just doesn't make sense, and I'll come back to that. So we basically, partly we're just saying, yes, this approach of taking different sources of evidence and bringing them together with expert judgment is an appropriate point. There were some pieces around we're not getting into the weeds of this process. It is true that there isn't a lot of specificity in this preamble document, and so we sort of did say that some amount of increased transparency would be useful. But overall, and again, I'm going to get back to the statistical takeaways, we sort of concluded that this framework could be used for health and welfare, and that it was a reasonable approach, but perhaps some tweaks around the edges might be useful. But let me turn a little bit to sort of takeaways that I think are relevant for our world. Again, one is that this is an incredibly, well, I say complex environment here. I don't mean environment, like climate environment, I mean scientific environment, where, actually I'll just go to this slide. It's a context where, again, they're sort of trying, Marshall alluded to this, trying to say, like, is there a link between, you know, lead exposure and mortality, or some pollutant and some outcome? We have biological mechanistic knowledge, like there is knowledge, like scientific understanding of links of things in the body. There's also large-scale epidemiologic studies. So Francesca and others have done large-scale assessments of causal links between exposures and outcomes, like at population levels. There's sometimes case reports where there might be like individual things that happen, I'll say more on this in a second, where there's just sort of a formal anecdote. And then occasionally there are randomized trials, but again, as Marshall alluded to, like, yeah, we're not going to put people in a room and turn the temperature, you know, comment on this room, but in general, but there might be, you know, there are some randomized trials of a environmental thing where maybe they actually do some experiments in like a field like sort of more lab setting. So it's a really interesting case because I went in sort of with my little like non-experimental studies kind of lens, but then you realize that for these broader sort of causal questions, it's really about kind of these different pieces of evidence. And I will say I've served on a similar committee, I wasn't the chair, of looking at the effects. This one was funded by the Department of Defense because they were concerned, some veterans were concerned that anti-malarials were causing later psychiatric symptoms, like many years later, like 20, 30 years later. And so we did that one, we actually did a review of the evidence of sort of digging into the studies. And yeah, there it's like, okay, we've got this piece of evidence and that one. And in that case, there were like individual case reports for individual veterans who were like, hey, I took anti-malarials and then 15 years later, I had a psychotic break. And, you know, and sort of trying to establish links. So there's like just a complex environment of information. There's also, and this was like a lot, I was honestly kind of surprised, a big conversation on the committee about what do we mean by causality. And some of like yesterday, like causes of effects and effects of causes. And even just getting sort of a common, we have a whole chapter now in the report on like what is meant by causality. I get, you know, no offense to our study team committee members, but they came from a variety of fields, a variety of backgrounds, like some very basic understanding that I would think most people from public health medicine would have about confounding very basic information about study designs just was not part of their skill set. So again, like in part, it was sort of another reminder that like we might be here like arguing about like this or that, but there's a whole set of important decisions being made. And again, it's nothing, it's just training and sort of that people have different sort of exposure and training. I think if I have like 2 more minutes, I want to make a quick comment on the bottom. So I will say at Hopkins, we've started teaching a course called Causality. And this is in the School of Public Health. And we have one person come each week from a different department. And I've sat in on the ones with the lab departments presenting, because we have 3 lab departments. And it is fascinating to sit there. And I'm coming from what I think of as like, this is the definition of causality. And they just have a completely different orientation. So anyway, I think we need more of those sorts of conversations happening. So again, I just wanted to like partly prompt a little bit of thinking about how we as statisticians can contribute to this world of integrating evidence. A lot of what we've talked about is individual studies and sort of how do we do them as well as possible. But there's huge need for careful thought about integrating. I've also quite involved in a few evidence clearinghouses in sort of the social sciences where they kind of come up with guidelines of like, is this quote evidence-based? Based on things like, what was the attrition rate in a trial? Or were the standardized mean differences less than 0.2? of a non-experimental study. Like things that we would view as very arbitrary, but in this world, they need guidelines to sort of come up with sort of some understanding of study quality. Anyway, I could talk much more about that, but I won't. I did just learn about this whole, has anyone heard of living evidence? Yeah, like I just learned about it last week through some conversations with folks at Arnold Ventures, where the other challenge is timeliness. So we can all also like be thinking about study quality and how does that sort of convey towards the decision making, but also how do we do that in timely ways? I think there is some people trying like ChatGPT kinds of things for this, which makes me a little nervous, but I'm sure there's a place for it, and I think we need to figure out kind of how to do that well. And I think statistician, like, or we are not all statisticians, but folks like with the expertise in this room, I think should engage so that these studies can be assessed well from a causal perspective. So that's sort of what I wanted to end with, were these questions, which is like in these things where we're trying to sort of integrate all sorts of evidence of different types, how much of this can be automated, you know? And actually I was thinking yesterday it would be fun to do a little experiment where if I send you all 4 studies, you know, and have each person sort of rate them, I am curious how consistent our responses would be. And I don't know, I think there might be variation in that. So then I worry about how would sort of ChatGPT, like if we don't have agreement on the sort of labeling essentially, how will AI tools do that? And I think sort of this idea of expert judgment, like on this evidence clearinghouse I'm on, we will sit and debate a randomized trial for 20 minutes thinking through like the attrition, like how much do we think that it's related to the outcomes? And just sort of, it's really hard to just automate that by like percent attrition. Like you sort of have to understand the context and to know how much bias might there be. And then the second bullet really relates to some of the themes from earlier too. How do we sort of ensure that we have transparent findings and that we can communicate the methods so that a whole variety of users can use them for these purposes? And how, again, sort of should we contribute to these really important policy and practice questions? So some questions, and I'm happy to continue the conversation. So, thank you.
Here, I don't see it here. What have I done wrong?
Oh, we can come back to that.
What have I done wrong?
It's two screens. We have to. Okay. Okay. If you prefer to see this on here too.
Oh, I don't care. Sure. Can it be on both?
Do the duplicate.
Sorry, I messed it up. All right, I failed.
Does he have a PDF?
PDFs are just.
That was that's the problem, that I have a PDF?
No, we have those screens that we could eliminate. That was simplified.
Sorry, everybody.
It's not for you.
Well, while this is getting set up, I can say I'm really happy to be here. What I was going to try and play.
Merge the screens. Maybe we can have a.
I think I did break it.
Because also in the afternoon we will have both
PDF.
It's also okay if it's just on the big screen. That's fine. Will I be able to just make it bigger?
Oh, I see. Okay, now I'm going to do
Okay, so I'm going to have to sort of orient myself so that I can see what's on there. Okay, so thank you everybody for being here. Thank you for the introductions, and thanks to Marshall and Liz for setting the stage here. What I was going to try and do here is sort of under the umbrellas that both Marshall and Liz described, try and talk about at least my thoughts on some fairly generic methods problems that come up, or at least ones that I've thought about to try and stimulate this discussion here. So the first one is this distinction I want to make between measurements or data, what I would call in a traditional sense, and data in quotes. Because if I were really trying to be provocative, I'd say there's no data in climate and environmental science. Now, I don't really believe that. But what am I talking about here? So when we do these types of studies here, sometimes we are talking about what I would call data in a traditional sense. Like somebody puts a machine outside and it measures some physical thing that's in the air, and then we know what the air pollution is there. It's an actual measurement of the thing we want. More and more often, at least as I've seen in this area, a lot of these climate and environmental phenomena that maybe we want to think of as exposures, they're not easily measured directly, at least not on a large scale. So often what we're looking at is something that maybe originated with some physics model, sort of like along the lines of what Marshall might have been talking about. Maybe it's combined with some sparse measurements, or really it's probably combined with some proxies of things that are sort of related to the thing we wanted to measure. It's probably put through some statistical or machine learning processing pipeline, and then we get numbers. And those are, I think, often treated as just data, as though those were the things that were measured, and that's not what they are, right? They're these complicated combinations of things. And so some examples of exposures or things we might wish to be interested in and use in these analyses are wildfire smoke. It's very difficult to measure what pollution comes exactly from wildfire smoke on like a national or a global scale. Marshall knows a lot about that. People are using these climate projections that Marshall alluded to. These are numerical outputs. They're using them as data. And they're not exactly that. Lots of things that we're using now are actually retrieved from satellites where they're not actually measuring the thing. They're measuring some reflection in the atmosphere, and then there's some algorithm that sort of converts that to the thing that we want to measure. Meteorology is similar. And then, especially in the climate change area, there's a lot of interest in sort of exposure to heat. But like, what exactly does heat mean, at least, let's say, from an epidemiological sense? Is it the temperature? Is it the humidity? We can measure solar radiation. What's going on? What are people exposed to when they're indoors versus when they're outdoors? I mean, these are all really complicated things. And people make various decisions, and then we get a number, and then we say it's data, and we just sort of move forward. And that, I think, should give us a little bit of pause. I think it would be simplistic to say there's just measurement error here. I think the issues are a lot more complicated than that. So I wanted to start with that. This is not a causal inference challenge per se, but I think it is a real one, and there are opportunities for sort of people who think about problems like we tend to think to make contributions here too. Okay, so that's the first thing. Another thing I want to bring up, which I think is an obvious distinction maybe in this crowd, but as I think it's still an underappreciated distinction in sort of environmental health, climate change, environmental epi, is the distinction between saying we want to know the causal effect of some exposure and saying we want to know the causal effect of some intervention, some action we might take to reduce that exposure. So just to give an example, if we want to ask a question like this, it says, what's the causal effect of exposure to air pollution and mortality? Like, this is what EPA needs to know, for example. You can think of a study where we measure where a bunch of people live, we measure the pollution where they live outside, we record when they die, if we do this on enough people over enough time, et cetera, maybe we can estimate like an exposure response function. So there are lots of important questions there. It's a separate type of question to say, number two here, what's the causal effect of an intervention to reduce power plant pollution on mortality? Here there's an action that can be taken at a point in space and time, and we want to know the impacts of that. Most of my sort of methods thinking has been in this sort of class 2, so I'm more biased towards these types of questions. But if you think about this, using an intervention on a power plant as an example, we can easily measure where the intervention occurs, and we can probably easily measure what happens to the emissions at that power plant. But who's impacted by that is actually a complicated question. Is it people who just live nearby the power plant? Probably not for that type of pollution. It's people who are sort of located downwind from that power plant. Well, how do you define downwind? So where should we measure mortality in order to assess the impact of this intervention that takes place at a point in space? So I think many of us have thought about, what I'm trying to sort of outline here is there's a very complicated link here between the intervention we can take, the exposure that we think is related to, say, health, and then whatever some health outcome we might be interested in is. And I'll try and say a little bit more about those links. So I still think this is an underappreciated distinction in this realm. And so I can't believe I'm sitting here putting the chain of accountability on a slide still 25 years later. This is in air pollution, this is like a very popular figure, at least it was a long time ago, but I actually think it's a good one. I didn't come up with this. The health effects
Institute did. But the reason I put it up here is, in this context, we might at the top of the slide take some action, and then there's like this cascade of things that happens before we expect to see some sort of health response. So we take action, the emissions change, the ambient air quality changes, people are exposed to something different, and there's a health response. This was for air pollution, but I think the same thing holds for other types of climate intervention mitigation analyses, where what's going on here in the middle is remarkably complex. This is like atmospheric science here, right? What happens to the atmosphere when you take an action to change emissions at these 100 places or something like that? And so one of the ways that I think it's possible to sort of address this in terms of causal inference methodology is to sort of make some use of knowledge coming from other domains that are more about physical modeling than they are about like empirical modeling. And Marshall alluded to some of these models too. So I think where we need to go with this is some sort of combination of statistical methodology and then things from more Earth system science or atmospheric science or geosciences, because of this issue where we have policy effects here that are going to be mitigated by or dictated by physical systems that might be reasonably well understood. And so we definitely do in this case need to account for how interventions at points in space spill over in the atmosphere. And so at a high level of abstraction, this was discussed yesterday in terms of social networks or markets or things like this. But here, the phenomena that drive that network, those like interrelationships among places, interventions and outcomes, is dictated by this physical process or some atmospheric process. And maybe we know a lot about it, and maybe we don't. And in my own work on this, I've tried to pursue both statistical solutions to try to understand like how does this spillover happen, and also more engineering-oriented solutions. I think there's a place for both of these things in this area. And I think one of the places is, at least in the sort of causal inference methods, is more of a foregrounding of spatial methods. So they came up a little bit in the discussion yesterday. But I think that these, there's a long, long history of spatial statistics research. And I think it's still very underutilized in causal inference methodology. And I think a lot of the questions in these climate and environmental policy, they're inherently spatial questions, or either the data are or the questions are. And so we have a lot of data that's coming from satellites, or we have gridded numerical outputs across the world or the country or something like that. And there's a real salience of this sort of these atmospheric processes that I keep alluding to. Things are moving all the time in space and time. And these processes are often baked into some of the causal inference questions we might ask in policy or mitigation. And I think in terms of the statistical terminology that we might be more familiar with, it's spillover, spatial spillover, or network interference. And I've put very small on the slide here spatial correlation, because I think there is a tendency to say like, oh yeah, we know that there's spatial methods for spatial correlation. And like that's true, and spatial correlation is a real issue. But that is not really what I'm talking about here. I don't think that like unaccounted for spatial correlation in the data is sort of the main missing thing from this literature. I think there are lots of other things from spatial statistics that are a lot more important. So I think this is a growing area, this combination of spatial statistics and causal inference, but I think there's a lot of room for growth here. So I want to just put a slightly finer point on this by illustrating a couple of things I've worked on. Again, still trying to be fairly generic, but make it a little bit more concrete. So I mentioned power plants before, so we have a bunch of work looking at impacts of interventions on power plants. So here's a power plant. They emit lots of air pollution. They emit lots of greenhouse gases, depending on their fuel. There are lots of policies and interventions to reduce emissions at power plants. And so if we do that, we intervene at some power plants to reduce emissions, it sort of kicks off this change in atmospheric conditions or atmospheric processes. That changes what people are exposed to, and maybe that changes some health outcome. And so the fact that it's power plants is not that important here. I think this is really kind of a generic challenge for saying we have the sources that actually put the air pollution into the air. Those are located at points in space. We're going to intervene on some of those points in space. But then we want to know how the outcomes kind of spill across the whole continent or the whole globe or the whole area. So I had I don't think this is going to work. I had an animation here, but I was prepared for it not to work. So if that animation had worked, this yellow triangle is the location of a power plant. I'm just trying to give you a sense of the spatial scale here. And this sort of trajectory that's put here is, it doesn't matter exactly where it comes from, but it's sort of an illustration of where, when the pollution leaves that power plant, where it goes. And that's just where it goes, like, over 12 hours. So what the animation was like, basically picture that line kind of wiggling around every few hours. And like, that's what we're dealing with here when we say we're going to take an action at some point in space, a power plant. The impacts, the spillover of that action might happen on a scale like this. So I think that's a really, so sort of getting a handle on how this works is a key challenge here if we want to ask something about, say, the causal effect of intervening here on some mortality outcome that's measured, you know, all over the country. Something like that. And so we've sort of termed this as causal inference with physical process interference, just because it looks a lot like what's going on in other network interference settings, but the challenges are, and I think the corresponding methods are a little different. So that's sort of one challenge, and as I mentioned before, we've pursued sort of an engineering approach where basically we try to make use of some of those physical models that exist in the literature and use them, try not to take them too seriously, but still use them and then sort of fold them into a causal inference approach. I think there's room for that. And then we've done more of a statistical, like almost purely statistical approach to this, where we say we're going to estimate the structure of that spillover. We're going to estimate those atmospheric dynamics, and we're going to estimate that with a statistical model that's sort of baked into our model for estimating causal effects, propagating uncertainty in that physical process into our downstream causal estimates. So we've sort of done both of these. I think there's space for both types of those methods in answering these questions, but certainly a lot of development to do. The other challenge I wanted to try and, again, just sort of highlight in a generic way, this is more about confounding, what I've called spatial or non-local confounding. And so here's an idea where we have a blue dot here, which is a point in space where there's some intervention, let's say, or some intervention may or may not be adopted at that point in space. And we have, as potential confounders, gridded estimates of, let's say, many meteorological factors. Think like humidity, temperature, things like this. And those are available at grids. You can sort of see the pixels here in the picture. And we know that meteorology confounds the relationship of the intervention at this point and some outcome. We suspect that. But the question is, the challenge is meteorology is not an inherently local thing, right? If we're trying to characterize the meteorology at a point in space, it's not just what you measure at that point in space. It measures like kind of what's going on, because we know this is a sort of, we're just getting like a snapshot of the spatial process, basically. And so we sort of formalize this as what we call non-local confounding. It's kind of in this, what's illustrated in this picture here, if that's our intervention point in blue, the shade of the orange there is meant to indicate how strong confounding at that, how strong meteorology at that other location might confound the relationship at that blue point. And so we had some stuff that we did to try and obtain a map like this. It's not that important, but the question is, we say, okay, if we have some causal effect we want to estimate at this point, sort of where do we have to look for the confounding information in space? Because it's probably not just like the nearest neighbors or something like that, because it comes from this process. And so we had a way where, like, if you just to explain this a little further, you know, the confounding is strong right around that point, but there's also some pattern here where the confounding here is stronger than it is even at locations closer. So this is not just like a spatial proximity thing. So I don't know, hopefully that paints at least the picture of the challenge, is how to learn how confounding works in settings sort of like this. I think that was basically all I had to say, sort of remind us all that we need to make careful use of things that are not strictly speaking data, but are these data products. I do think there's a lot of room to advance methods for spatial causal inference, explicitly spatial causal inference. I think we can make some effective use of physical process knowledge from other domains, in this case sort of atmospheric domains. And then I tried to sort of generically outline two methods problems that I and others here, Fabrizio, Laura, and I have worked on. I think that's it. Thank you.
So what we're going to do, I'm going to just provide a little of summary, and then I'll try to be highly provocative question for the three panelists to get the conversation started, and then we will open to the audience. So first of all, thank you all. I think it was fascinating how you you three provided, I think, different and highly complementary perspective about causality in the context of this highly contention environment of environmental and climate policy, right? So to summarize, we had, and this is regardless of whether or not it's the area that you are working, but I'm just summarizing the perspective that you provided, right? So actually Marshall provided a beautiful distinction between, and going back to the conversation we had yesterday, between the causes of effect and effects of causes. Because when he talked about attribution and when he talked about how likely is that the hurricane that happened yesterday is due to climate change, now I'm going to have it mix it up. But this is about the causes of effect. And then he talks about what he's working a lot is what are the consequences of extreme weather event on health, and that is the effect of causes, right? And so you also see the tension in the climate science space between these two, and sometimes this can become really, really a very important tension. Leads through our experience of chairing this panel, which there was a monumental amount of work, Liz, and their leadership really shined there. Basically, she's providing also, the lesson that she learned on the panel, we all learn on the panel, is that when you're dealing with a very consequential and contentious question, the weight of the evidence, and basically building consensus about different sources of evidence and assessing causality, it's, really ultimately is the one that matter. And Corey, throughout some of his perspective and some of the work, really highlighted in the context, again, of this space of environment and climate, a lot of the really serious methodological challenges in causal inference that we still need to overcome, from error in the data, spatial interference, spatial temporal processes, local and global confounding, and so on, right? So I'm claiming, and I'm going to make a little jump here, that some of the challenges that you see from the distinction between effect of causes and causes of an effect, weight of evidence, methodological challenges are not only unique to the field of environmental and climate. I would say that if you have a very contentious question about education, about social sciences, about biological sciences, we're going to have the same type of discussion. You're going to bring, experts that will think about different things. And so what I've been learning about this symposium here is that if I'm thinking about it, and I'm going to get to the question, I promise, is that if I am a computer scientist, right, we learned yesterday, we are now really interested into developing causally aware machine learning model, causally aware AI model. If I am an economist, right, it's really important thinking about what Guido presented yesterday. Well, some of the questions that Marshall presented on the effect of temperature on mortality are panel data, right? And you're really interested about the IV, the measure confounding. If you're a climate scientist, you're interested about attribution. If you're a policymaker, you want to get policy consensus. You want to get the weight of evidence. And if you are a methodologist in causal inference, you want to get a new approaches for network interference. Okay, so I want to solve the problem of, I want to address a really important question. Does exposure to air pollution increase mortality? Does exposure to causal related to increase of mortality? But just think about any causal question. And I'm going to give you, each of you, $1 million. How much of this $1 million you're going to spend into machine learning, causal inference, AI model, new causal methods, new approaches, new philosophical approaches of this causal effect? Choose. Tell me how you're going to spend this money. Marshall.
Oh, God.
Data, anything. You have $1 million and you want to get to the bottom of the question, how are you going to spend this money?
In 15 seconds.
Someone else can go first. Yeah. Luckily, we have more time to write grants.
So
anyone can start.
What I would say to that specific, well, so it's hard to think.
It's hard to think.
Always.
He's smiling.
I know. For that specific question, does pollution cause mortality? I mean, I think the question actually is important because for that question, I mean, we're talking decades of evidence. Just as Liz said, right? Like that's what that report and the EPA does. Decades of evidence, different data sets, different perspectives, different parts of the world. You know, from toxicologists who are putting people in rooms and pumping them full of air pollution to see what happens to these like large-scale epi studies. And I'm not sure that the main challenges there are methodological. I think they're more sort of what Liz was talking about. That was more how do you synthesize all of this evidence from all these different perspectives, make the case, and provide something that a regulator then can come and say like, this is what we need to do. So maybe that $1 million goes into figuring out that process, at least in the case of like particulate pollution and mortality, because we know a lot. But you could have posed a similar generic question that was about, I mean, I don't know, something that's also well studied but maybe not as well studied, like heat and health, or something that's like a lot less studied than that, and then I think the answer might be different.
I was going to say the same thing that, well, although with a twist, I might say spend 2/3 on a very thorough, very carefully done evidence synthesis with like good experts in the room going through each study, but reserving some for the gaps that might be identified, like using the evidence synthesis to review the existing evidence, but also to say, like, is there an additional piece that is missing? And sort of reserve some funding to be able to sort of start towards that. So building, essentially a way to build on what would already be known.
And by the way, I mean, the air pollution mortality, because it was the first thing you came up with.
Yeah.
I guess I would try to go after what I see as, in this specific area, a remaining piece. And Francesca's worked on and done pioneering work on this, but really understanding the relationship between long-term air pollution exposure and mortality outcomes, which is really hard, right? So if we're looking at short-term exposure, we can think of a lot more randomness and variation that you could exploit to understand the impact of short-term exposure. Long-term exposure, decades of evidence suggests that through various economic, sociological processes, different groups get very different exposures to air pollution, right? And so you have so many correlates of air pollution exposure that also determine mortality outcomes or any outcome that you're interested in, that the confounding problem is fundamental here, right? And there's been progress on this. Again, Francesca is a leader in this field, but so, you know, as an economist, you really want to try to exploit some sort of natural experiment or policy-induced variation in long-term exposure. And there are some designs that have done this, but I don't think we've completely cracked the nut on this, or maybe we've exhausted what we can do in the US. We know very little in developing countries where exposures are a lot higher. So I actually think there's a lot empirically still to do. How I would spend $1 million exactly, I don't know. So I don't know if I can answer your question, but.
Okay, I'm going to ask another question, and then I promise I'll stop. So,
you need the mic.
We are now in the world of artificial intelligence, whether we like it or not, right? And so, to all of you, what do you see the potential, but at the same time, you know, the challenges, opportunity to leverage this new world of AI, whether it's both like AI/machine learning or generative AI, and how do you think that this scientific revolution, I would say, and technological transformation is gonna inform the work that you are doing? Corey, I'll start with you.
Start with me. Hi.
By the way, I didn't tell them the question.
Yeah. So I would say a couple of things. So one thing, I guess if I were a little more savvy, I would have said that was an AI approach. But like that map I put up there, that was a latent representation from a deep learning thing. So it was not a particularly modern or sophisticated one, but I do think that there are situations in which the sort of latent representations that underlie those AI methods that you maybe don't even necessarily need to interpret, may be able to, represent some of these complex things that come from satellite imagery and meteorologic fields and all that stuff. I think there's potential there. I thought I had something else constructive to say in addition to that, but maybe, yes, I do. So I also know and again, I'm like a little out of my depth here, but in more kind of explicitly AI large language model type approaches, there's some action in the climate space that I know of it's mostly about forecasting though. And so it's not about asking causal effect questions, but it is using some of the same data set, climate projection data, et cetera, and learning how to, sort of prospectively forecast extreme events or changes in temperature and things like that. So I think that there's some action there that could, I think, be oriented towards more explicitly causal questions.
Liz?
Yeah, I'll expand on, I'll stick within the sort of evidence synthesis piece. This weight of evidence approach, which again, it sort of combines like a formal review of the literature and sort of formal assessment of individual studies with kind of sitting around a table and talking about, like experts, talking about that summary. It is incredibly time consuming. I mean, the EPA spends huge amounts of time and money to do one of these, and they need to do a bunch of them. And so I would be interested in, I think there's ways, I am skeptical of the sort of the final kind of weight of evidence in terms of how do we weigh confounding and this, and when do we know if something is sort of a fatal flaw versus just a limitation. I think that is hard for some of these approaches, but I think reviewing the evidence, basically making it easier for the experts to spend their time on the kind of conceptual challenges, whether it's through finding the papers, maybe also through summarizing the papers and pulling out kind of, instead of having to read 30 pages, pull out kind of key aspects. So I think sort of automating the process and then bringing in the sort of basically helping figure out what are the pieces that can be automated, but then also and then using sort of individual experts' time as well as possible to make the whole process more efficient.
That's a good point. Marsha?
Yeah, I agree totally with Liz. Yeah, our group has experimented with these AI tools to try to do evidence synthesis, and yeah, it's a bit of a mess right now. Certainly in finding and combing through large sets of papers is helpful in terms of the models being discerning about what's a good paper versus not, or strength of evidence, they're still pretty bad. Yeah. My guess is that will change pretty dramatically, and so we need to take seriously and experiment as much as we can with these tools. So I totally agree. The second one, an area where I've worked with colleagues in computer science, is computer vision has really transformed our ability to extract useful information from a range of non-traditional sensors. So satellites being the main one. But the world has just fundamentally changed in our ability to use satellites to measure environmental-related, human-related outcomes in the last 5 years. The architectures get better and better, but they're already quite good enough to be able to make a lot of progress on air pollution measurement, on various types of human activity that are otherwise hard to measure. So I think this is transformative in terms of being able to put together comprehensive panel data sets, on which then you can hopefully do causal inference, caveat all the important measurement problems that Corey brought up, which I think are really important and we've only begun to grapple with, I think, in this context. But I think the transformation there for environmental questions is at least as large or larger than the large language models.
Question? Do we have a shy audience now? Are you hot? Are you ready for lunch? Any question?
Okay, so I want to make one comment and then ask a question. My comment is that I'm really struck by how the range of problems having to do with the environment are the same problems that have to do with everything important we study. So there's nothing special going on here. But my question is the following. In the conversation, it seems as though there's a consensus that consensuses of experts can be useful in evaluating large bodies of complex evidence. in political science, the work that I've seen, there's not very much, but the work that I've seen on the use of expertise is just appalling.
Yeah.
We suck. And I mean, like, give it to an expert and you learn less than if you didn't talk to the person. So it's negative knowledge. So, I mean, really, a computer does better than we do. So AI does way better than what we do. Lasso does better than what we do. So what I want to know is, like, are we just particularly, we're not stupid, but maybe we have particularly challenging problems. Do we have more challenging problems about which fewer parameters have been established? Or could your recommendations about expertise be equally problematic and you haven't thought about it?
Yeah, no, that is a great question. I'll tackle this because we grappled with this on the committee. And one of the things, I should have said this in my talk, one of the things I was really surprised by is how little this world at least knows about group decision making. And actually one of our recommendations was there should be more research on group decision making. And yes, like I had the thought experiment in my head, you know, National Academies panel, like this is how they all work. Like the antimalarials and psychotic symptoms panel, I was like, if they had had 20 different people, would they have come to the same conclusion? And no one knows. So yes, I mean, I feel this tension where I am still skeptical in a causal world. Given the untestable assumptions in our causal studies, in most of our causal studies, I am pretty skeptical that there's no role for expert judgment on sort of study quality. So that's where I would sort of, I'd be curious to learn more about the literature and if it's examining that question, because maybe we should just throw it all to an AI model. I'm skeptical of that particular piece of, like that's where I do think expert judgment can be useful, but I totally agree that there should be, and I think there are fields that do this a little bit, but they don't talk to the other fields that are actually doing it in practice. And so if we can figure out, maybe the research synthesis community can do that, but I think it's a great point.
Great. I'm going to go to Andrea and then I'll come to you.
Mine was just a curiosity on the causes of effect, so provoked by Marshall's presentation. So CO2, human emissions, but do we know if it is more a problem of world population or emission per human being? The question is actually a personal family question. I have a child who says that doesn't want to have kids because the world is overpopulated. And I'm suggesting the possibility that the problem is not to reduce population, but to reduce emission per person. Is there any evidence on this relative responsibility?
Yeah, it's a good question. Certainly, more people on the Earth leads to more emissions. More wealthy people on the Earth probably leads to more emissions than just a marginal additional person anywhere, right? So I think the hope in approaches to reducing emissions is not to make fertility decisions for people, but to figure out technologies that will allow us to sustain whatever decisions people want to make without emitting or with, you know, reduced emissions. There's as you know, a sort of sordid history of discussions around population and what should happen with population, and so I think most climate scientists try to steer away from that to the extent they can. So I'm not going to take the bait.
Turn a contentious topic even more.
Right.
My question is, how do you deal with trust in your findings? Because I know like Carbon Observatory and all that, they did great lengths to make sure they document where did every fact come from and how do you put things together. So what's the approach to get people to believe what you say based on your excellent causal research and knowledge synthesis?
The question was around transparency and how to help trust and sort of how to do studies in a way that leads to trust and transparency. This was one of the other recommendations of the report, actually, which is that I'll just talk about it with that NACS process in mind. But yes, right now EPA's process, we sort of agreed was reasonable, but it wasn't super transparent. And so to that point, kind of wanting to trying to push to be a little more transparent so that then it could be more trustworthy. So that was discussed in our report for individuals.
I mean, I don't have that much to say about public trust. I mean, one thing that I learned pretty quickly working in this area, I learned from Francesca working in this area, I'll say I got a lot more careful myself in terms of things like reproducibility, and especially when you're bringing together a bunch of data sets and you're doing that data processing yourself or somebody in your group is doing it, because you can get audited. Like that's just a thing that happens to people doing research in this other areas too, right? But like, but if you are not careful and organized from like a reproducible research standpoint, it can really, really come back to get you if you're going to publish something that says, power plants are killing people, or, greenhouse gas emissions are killing people. So that's not really public trust. I don't think that's really what you asked, but I think it's sort of related, and that's where my experience is, at least.
It's certainly a challenge in the climate community. You see a lot of people, I would count myself in this bucket, convinced that certain courses of action are better than others in terms of what we do about climate change. And to some, that points towards advocacy, and you see climate scientists becoming advocates for a certain political position. There are also studies, I think, very clearly suggesting if scientists do that, it erodes their trust, the trust that, I think to your question, that the public has in them. And so people have made very different choices around that, but it's really important. So I think the social science research would suggest that if climate scientists or other scientists want to maintain the public's trust, they should not be advocates. I think that's what that suggests. However, when you work on a problem like that, it's hard to not want to be one. So there's a tension.
Thank you for the nice talks. I'll follow up on the causes of effect thing from Marshall as well, because you raised the question to us, but when you showed slides with evidence, it was about CO2 emissions and climate change. So that's much more specific, and maybe the way I interpret it is the effect of CO2 emissions and climate change, not whether or not humans led to climate change. And the other thing, but I want to follow up on Francesca's point too, because the other image you showed was the one where there was a flooding, and the question was the flooding caused by climate change, whatever that means. But is that the right question to ask when the flooding has happened, or is it what can we do to prevent future floodings, or what is now the probability of future floodings? And you can say, well, in legal cases, they will sue people because they did illegal emissions that led to a flooding. But shouldn't they just be sued because they did illegal emissions anyway, regardless of that led to flooding, if you want to prevent it in the future? And if they were to be sued for that, that's just a question again about effects of causes and not causes of effects.
Yeah, thanks. Yeah. I think there's different ways to frame the climate change question, the what's causing climate change. It is sometimes framed in the causes of effects. So global mean surface temperature has risen by 1.3 degrees. Is human emissions responsible, right? And I think people literally try to answer that question. That's sort of a causes of effects. I framed it as in the other way, or emissions causing this, but basically when you run those model experiments, you take out all the emissions and you basically explain the entire increase in temperature. So in some sense, maybe it's an effect of causes, but you have one cause and it explains, or you have one cause and it explains everything. So it's a sort of a tricky one. On your floods question, yeah, I agree. So there's a huge enterprise among climate scientists to try to do this attribution, to say how much was an individual event, the probability of an individual event changed by a warming climate. I am with you. I don't, or I'm with the tenor of your question. I don't necessarily find that useful. I think it's more useful to ask, how do we reduce the impacts of a flood? That to me is the more interesting question going forward, instead of trying to look at that, squint at the tails of an extreme value distribution and estimate how the probability of something is changing. Which requires strong assumptions anyway. I'm with you. For the legal cases, these suits brought against this evidence turns out to be important. It's certainly been used in these cases, and so it's part of the science. But I'm with you on that. That does not, to me, feel like the most important question.
Can I add one quick note? I think next time this happens, we should invite some legal experts, because causality in the law is like a whole other thing, which raises these tensions. So that would be a very cool conversation.
I'm not the expert of causality in the law, but just about this conversation, I do think that we always have to keep in mind that often in a legal environment, the causal question is formulated in a way that you cannot address it. So then you win your legal argument. And so I think as a causal inference expert, sometime before going after and addressing that question, we need to ask ourselves, is this the right way to posing that question? Because that's where the manipulation goes. So anyway, Kosuke.
Yeah, thanks. Corey, I have a quick question for you. So you mentioned that there's a sort of physical model that explains how the pollution spreads. I'm just curious, so I guess on one hand, it's not locally concentrated spillover effects, so the spillover effects could happen in the long distance. But on the other hand, if those models are actually useful, you know a lot about which direction or approximately which areas. So I'm just curious how, you would incorporate that. I've done some work on spatial process, and for us in that particular application, we sort of black box the outcome spillover effects and just model the propensity score. But here it seems you can incorporate, a lot more about how the spillover effects are, happening.
Yeah, we've done a couple different things. So for those who are familiar with the network interference literature, there's a big literature that relies on some sort of exposure mapping that use some function for how you drop treatments on some nodes of the network, and then sort of what is the inward impact of your friend's treatments. That's sort of the more traditional framing. So we do something like that. But that function that we use for the exposure mapping, say, might be entirely informed by the outputs of this physical model. So so we've done it two different ways, right? So one, it's a physical model where they're not estimated, but that's more of a computational engineering model. We validated it over many years. It's a pretty good model. It's not something that we just sort of cooked up overnight. But there's no uncertainty. There's no estimation there. You just get a number, right? And that's just fixing the network in your network interference study. And that was what I was referring to when I alluded to the engineering approach. We do this model, we take the number, we stick it in, and at that point it's like data on the network structure. The more statistical approach to that is a stochastic partial differential equations based spatial process model. So that all is estimated with uncertainty, but in terms of how it's incorporated into the interference, direct, indirect effect estimation, it's the same exposure mapping paradigm. It's just that instead of getting one characterization of the network structure, weighted network structure, you sort of sample from a posterior distribution of network structures. And so that's a statistical model. You get all the uncertainty. It's not as good as the physical model, at least not for the particular type of pollution source and the particular type of pollutant we were looking at, but hopefully that's a baseline that we could build on to get the statistical model with uncertainty kind of closer to what the more physical model might tell us.
So last question, quick answer. Caleb, you have the last question, and then we'll break for lunch.
Thanks. I think this is not a terribly well-posed question, but it seems the kind of most devastating impacts of climate change are not so much kind of people die more when there's a higher temperature, but these extreme weather events, I guess the flooding is one example, and then drought and famine and these kinds of things that seem these are things that we don't have a lot of data on, and we're really kind of extrapolating when we're envisioning these things happening. So I just wonder how you think about that, and when we think about like climate adaptation, is that well informed by these estimates of like mortality, you know, at extreme temperatures, or should the focus be shifted kind of elsewhere?
I'm going to get to Marshall maybe for a quick answer.
Yeah, it's a great question. I think there's a lot of climate phenomena whose impacts we still don't understand that well, and a lot in the developing world, just because we don't measure either the exposures or the outcomes that well. We don't have a great handle. We think things are bad, but in a quantitative sense, maybe we don't have a great handle. We also, again, on the intervention side, have had very little experimentation on what works. To me, that's the important thing. We know droughts are bad. Generally, right? We need to know how to break the link between a drought and lower incomes in agrarian society, to say. Again, there's been some experimentation, but it really lags, to make my point again, what we know about mitigation. So, super important point.
Well, join me to thank the
I wrote down multiple things to ask you about.
Oh, same.
Your description.